Hi, it's time for another math easy solution. Today we'll discuss a new topic, and that's going to be on infinite sequences, and then go over limits, squeeze theorem, Fibonacci sequence, and the golden ratio, plus much more in this very extensive video. And just a note, as always, if you don't have time to watch this whole video, you could play this video at a faster speed. Yeah, there's no summary and conclusions, so it's not applicable for this video. But yes, play this video at a faster speed. I highly recommend using this browser extension. But if not, you could use any one of these other methods. But yes, top secret life hack, your brain does get used to faster speed. It's actually quite amazing. And also you can download and read the notes or view the notes on Steemit in article format. Hashtag get on Steam. The links for both will be in the description below. But also you could watch this video in parts, so it doesn't need to be all at once. But I'll be very impressed if you can watch it all in one go and if you can absorb all of the information. Alright, so now, before I get to the mathematics, I just want to make a quick MES update, just to make a note that this is the last mathematics video I make until I finally finish my much anticipated and game-changing hashtag anti-gravity part 6 video. These math videos take a lot of time and brain power to complete, in which I need for finishing part 6. And if you've been following along, yes, I've been making some videos on this anti-gravity topic, which is quite fascinating. And I will look to remove, I'll look to remove all distractions, hopefully have the part 6 video uploaded by the end of this year, and basically proving that both classical and quantum mechanics are at best short-sighted or at worst wholly wrong. Will send a ripple in the aether of duality, so expect the video to be pretty epic. And yeah, that's the reason I made that phrase, and that goes to my next point, MES top secret hint. It's no coincidence that the top 3 cryptocurrencies by market cap currently are Bitcoin, or in other words bit, which is just a 1 or 0 in computing, and which in other words represents duality, or good and evil, etc. And then ether is number 2, and that's the aether, or I like pronouncing it this way, and I'll explain why in part 6, and I like spelling it that way as well. And then number 3 is ripple, XRP, in other words, ripple in the aether of duality. And the XRP X logo is also in the shape of David LaPointe's game-changing primer fields video series. Make sure to watch that. Absolutely epic. And yeah, here's a key phrase, the ripple in the aether of duality. Remember that phrase, and maybe the order of the wording too for the near future, as that could impact the order of the top 3 cryptocurrencies, because I think Ripple might jump up ahead, at least for the short while. So anyways, enough top secret MES occult financial advice. Now let's go over some mathematics. Alright, so let's just jump right into the topics to cover, our table of contents, and it's going to be a super extensive video, so put basically outline of the topics and concepts and examples and so on that I will cover here. So let's go over this. So I'm going to go over initially introduction to sequences and series, and sequences and notation, go over example 1 and 2, and then example 3 will be an introduction to the famous Fibonacci sequence. Very fascinating stuff, so stay tuned for that. And the third part, I'm going to go over definition of the limit of a sequence, go over the precise definition, go over theorem 1, then definition of limits of infinite limits of a sequence, and then limit laws for sequences. And yeah, this infinite limits is when the limit approaches infinity, and so on. So we're going to go over the squeeze theorem for sequences, and then theorem 2, and then go over example 4 and 5. Example 6 will be on divergence, and example 7 will be on convergence, and yeah, they're pretty much interconnected. And go over theorem 3, then go over example 8, and example 9 is on convergence, and then go over quickly on graphing, creating graphs of sequences, creating graphs of sequences with a calculator, and also go to example 10, convergence, and then monotonic sequences. Go over example 11 and 12, and then go over bounded sequences, go over the completeness axiom, which is a very interesting axiom, and yeah, just introduction to some mathematical rigor. That, and pretty much anytime I deal with precise definitions of limits. And go over monotonic sequence theorem, and then go over example 13 on recursion and mathematical induction. And then go to end of chapter exercises. Exercise 1 looks at convergence, and then exercise 2 is proof of theorem 2, which I covered earlier, which I will cover soon, or listed above. Exercise 3 is on proof of theorem 3, and then exercise 4 is on the famous Fibonacci sequence. And then at the end of this video, like what I like doing is go over a mainstream history of Fibonacci. And again, I state mainstream. If you've seen my earlier videos, it's because Yeah, because I've realized that just because it's a mainstream or mainstream source or mainstream news site or mainstream science or mainstream university does not mean it's right. It just means this is what everybody else believes, or the quote-unquote consensus. But anyways, make up your own mind and don't just take anyone's word for it. But it's still always great to go over the mainstream to see what just general overview of any given topic. So now then I'll go over overview and mainstream history of Fibonacci sequence and the golden ratio. Go over Fibonacci numbers, golden ratio, phi or phi lowercase Greek letters like that. And relationship between Fibonacci sequence and the golden ratio phi, and that ratio is phi is the limit of the ratio of successive numbers of the Fibonacci sequence. So yes, the ratio of the successive numbers, remember that. And then go over the golden angle, golden spiral, and then they also golden ratio and Fibonacci numbers in all aspects of life, from nature, art, design, corporations, and even advertising. Hashtag amazing, amazing stuff. And now let's look at introduction to sequences. And so infinite sequences and series were introduced briefly in my early videos on Zeno's paradox and in my videos on infinite sums. So make sure to watch those if you haven't. And just MES note, recall that sequences are just ordered lists of numbers and series are the summation of these sequences. Just a quick example. For example, this ordered list 1, 2, 3, 4 is a sequence, and then 1 plus 2 plus 3 plus 4 is a series, so a summation of the sequence. Just do a quick overview of that, and I'll dive into precise definitions for the sequence and then the series in later videos. And yes, basically their importance in calculus stems from Newton's idea of representing functions as sums of infinite series. For example, in finding areas, he often integrated a function by first expressing it as a series and then integrating each term of the series. And yeah, we will pursue his idea in later videos in order to integrate such functions as e to the power of negative x squared. And recall that we have previously been unable to do this using just basic integration methods. So it's hard to find antiderivative for that. I'm not sure there is. Yeah, so then we'll do a numeric / series summation of sequences method. So many of the functions that arise in mathematical physics and chemistry, such as Bessel functions, are defined as sums of series. So it is important to be familiar with the basic concepts of convergence of infinite sequences and series. Yeah, and physicists also use series in another way as we'll see in later videos. In studying fields as diverse as optics, special relativity, and electromagnetism, they analyze phenomena by replacing a function with the first few terms in a series that represents it. And here's a small preview of some of the types of series and functions that will be covered in later videos. This is the partial sums Tn of a Taylor series provide better and better approximations to a function as n increases. For example, this one here is y equals sine of x. And then if the first T1 of the Taylor series is a straight line, and then when you add to that to another term of the series, you end up getting a better, or actually goes down this way. So you get a better approximation. That's T3. Then there's another, that's T5. Goes like that and goes down. Then T7 has an extra down as well, and then there. So as you can see, it gets better and better approximation as you increase the number of terms in the series. So just fascinating stuff. And then here, these are actually these are Bessel functions, these models right here, which are used to model vibrations of drumheads and cymbals, and they are defined as sums of infinite series. Notice how closely the computer-generated models, which involve Bessel functions and cosine functions, match the photograph of a vibrating rubber membrane. So yeah, this is actually quite amazing. This is just using sound frequency, and then the rubber membrane goes up and down, and you can model it using the Bessel functions. Again, those are just sums of infinite series. Very fast, and goes up and down. And in fact, this whole this whole phenomenon of this vibrating membrane or any sound frequency or vibration that makes amazing patterns in even just like putting salt on a frequency plate, or just a plate and then shake it according to frequency, and it'll show up in pretty geometric amazing patterns. And I'll go over that in later videos. I believe that's called semantics. It's quite amazing stuff. So yes, everything in nature pretty much looks like this shape. So let's keep going further, and now let's get into sequences. So a sequence can be thought of a list of numbers written in a definite order. So it's ordered list. So A1, A2, A3, A4, all the way to AN, and so on. But it's we're going to be dealing with infinite, so I'll get to that in a bit. So the number A1 is called the first term, A2 is the second term, and in general, AN is the nth term. We will deal exclusively with infinite sequences And so each term will have a successor an plus 1. So you're always going to have further and further. And notice that for every positive integer n, there is a corresponding number an. And so a sequence can be defined as a function whose domain is the set of positive integers. And we usually write an instead of the function f of n for the values of the function at the number n. Yeah, so it's pretty much a function, but for positive integers, but we write it this way instead of f of n. Alright, so if we look at the notation for sequences, we'll have this, the sequence bracket A1, A2, A3, keeps going on, and then close bracket can also be denoted by, or is also denoted by, writing it as like this, bracket AN, and then close bracket, or you could write it as AN, close bracket, and then you can include the parameters. So you can have it from n equals to 1 up to infinity. So this just illustrates that you're starting from 1 and then going to infinity, and these are all infinite sequences that we're dealing with. Yeah, so for the most part in this video, if these parameters aren't included, we'll just assume they are. You can just write that down like that. It starts from n equals 1 and all the way to infinity. Alright, so now let's look at a quick example 1, to illustrate dealing with this notation of sequences. So some sequences can be defined by giving a formula for the nth term. In the following examples, we give 3 descriptions of the sequence. One by using the preceding notation, and then that's this one right here. And then I'm going to write the other ones down myself. So this one, circle this. These ones will do right now. So another by using the defining formula, which is the one inside. And the third by writing out the terms of the sequence, writing it all out. So for the first one, for number A, we have n over n plus 1. And then from n equals 1 to infinity. So we'll have an, the defining formula is just an equals to n over n plus 1. And then we could also write this out. So if we were to expand this out, just expand this out, we'll have at n equals 1, we have 1 divided by 1 plus 1, that's just 1 over 2. And then when we have 2, and then 2 over 2 plus 1 is 3. It's 2, 3, and as you can see the pattern, it just goes higher. So 3, and divided by 4, and so on. So then it's going to be 4 over 5, and so on, dot, dot, dot. And then it's going to add the term there, n plus 1, and keeps going on, and close bracket. And now for B, for the same thing, we have right here, so the an is going to be the inside bracket. That's going to be negative 1n, n plus 1, and then 3n. So we're going to start again with n equals 1. If it's not there, we just assume it's, we're just going to be defining from n equals 1, from the first term. So we have n is 1, so when we have negative 1 to the power of 1, that's going to be, well, negative 1. It's an odd number. So negative 1, then we have 1 plus 1 is 2, so we'll have a negative 2 over, this one's 1, so 3. And then the next one we'll have, well, 2, negative 1 to the power of 2, that's positive, so that it's not going to have a negative sign. So if it's positive, make this thicker. So it's going to be positive, and then we'll have 2 plus 1 is 3. So positive 3 over 3 to the power of 2 is going to be 3 squared, and that is just going to be 9. And then going further, now when we include a, so the third term's 3, so negative 1 power of 3 is an odd factor, not odd power, so that's going to be a negative. And then 3 plus 1 is 4. And then 3 to the power of 3, that's going to be, well, 9 times by another 3, that's going to be 27. And then next one up is 4, so put that, that's going to be even power, so it'll be positive. 4 plus 1 is 5. And 3 to the power of 4, well, that's just going to be times it by another 3, it's going to be 81. You could also see it as, I'll put this like this, 3 to the power of 4 is just equal to 3 squared, which equals to 3 squared times 3 squared. In other words, we're just having a 9 times 9. Or a 9 squared, so equals 81. And so on. Then this goes dot, dot, dot. And then we'll have negative 1n, n plus 1, all over 3n. And then this is going to be, keeps going on, dot, 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 and close the bracket. Alright, so now let's look at C, which is over here square root n minus 3, then from n is equal to 3 all the way to infinity. So we have the a/n, the defining formula is one inside, square root n minus 3. And then the terms inside this are, so when we have n is 3, we'll have 3 minus 3 is 0. So 0, square root of 0 is still 0. And the next one up we have 4. 4 minus 3 is 1, square root of 1 is just 1. Next one is going to be 5. 5 minus 3 is 2. So we'll have a square root 2. And the next one we'll have a 6, square root 3. So 6 minus 3 is 3. And so on. It just keeps going on and on. And you can just put a square root in all of these. It won't change 0 or 1. But we keep going on, and then we get to square root n minus 3, and so on. It keeps going on and on. And now the next one is this one here is cosine n pi over 6 from n is 0 all the way to infinity. So the defining formula is an is equal to cosine n pi over 6. And then we'll just put all the terms in right now just as is with the cosine, then I'll evaluate it numerically soon using exact trig ratio. So we put the 0 in there, we'll have a cosine 0, then we'll have a cosine of pi over 6 for n is equal to 1. Then we'll have a cosine of 2. Let's leave the 2 over 6 there, or pi over 3. The next one here is going to be cosine 3 pi over 6, and then dot dot dot, keeps going on and on until we get cosine n pi over 6, and then dot dot dot, and then close the bracket. And now to evaluate this numerically, just for completeness sake, let's just first recall the exact trig ratios, and we'll do that by the equilateral triangle. So we'll have this like this. So I'll do this sides are 2, 2, and this can be 1, 1, like that. So it's equilateral. So the equilateral, the angles sum up to 180 or 60 in each. So 666 across, or in radians it's gonna be pi. So pi over 3. The whole thing sums up to pi, so pi over 3, like that. And then this one's gonna be, well, pi over 6. Divide that in 2. Pi over 6. Like that. So then the height here, this is just going to be square root 3, and you can recall Pythagorean theorem. Let me just write this better. And then what we should have is, well, the square root of this side 1 squared plus square from the then plus this side squared of a right angle triangle has to equal to, this will just be 1 plus square root 3 squared. It's going to be 3. This equals to 4. In other words, this is equals to 2 squared. So yeah, this is 2 squared. So that's the hypotenuse squared equals to the sum of the sides squared. And yeah, that's correct. And then recall that cosine. Cosine, we'll just look at these two numbers first. We'll look at this and this one. The other one we'll find it by graphing. So what we have is cosine pi over 6, that's this right here, is equal to, well, remember, it's just adjacent over hypotenuse. So it equals to square root 3 over 2. So adjacent over hypotenuse. So that's equals to square root 3 over 2. Yeah, so I'll just circle this one, just indicate that we got this point. So the next one is now, well, cosine 2 pi over 6. This just equals to, well, cosine pi over 3. So the 2 cancels with the 6, which is 2 times 3. So what we have is this equals to, now we look at the adjacent of this one. There's the angle pi over 3, so 1 and 2. Adjacent over hypotenuse, 1 over 2. Like that. And now what we need to do is get these 2 points. Cosine 0, cosine 3 pi over 6, which is just cosine pi over 2. And again, recall the graph of a cosine curve. Looks like this, theta, cosine theta, and it just goes down and up like that. And so on, there's 0, this point is 1, this is going to be pi over 2. At this bottom peak is going to be negative pi. I mean pi, not negative pi. and then this one's going to be 3 pi over 2, and then repeats the period of 2 pi, like that. So then at this point right here, this is just cosine 0. That just equals to 1. Then here, this is just cosine, well, 3 pi over 6. Where this cosine 3 pi over 6 is just cosine, well, pi over 2. 3 and 6 cancel out. So what we have is this, that's just equals 0. Like that. So we got this point and we got this point. So there we go. We go from a 0, this is going to be 1, this is going to be square root 3 over 2, this is going to be 1 over 2, and then we have 0, like that. So, yes, so that's what we have is, putting this all together, we have, thus, put the terms in together, we have 1 square root 3 over 2, 1 over 2, and then 0, and then dot, 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 all the way until cosine n pi over 6, and dot, 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 and keeps going on like that. And I'll just circle this answer like that. So there it is. And now let's look at another example, example 2, and it states find a formula for the general term an of the sequence, and we're given 3, 5, then negative 4 over 25, then 5 over 125, then negative 6 over 625, then 7 over 3, 125. Notice the 5s, notice the switching of the signs, and assuming that the pattern of the first few terms continues. So let's look at this. Note the pattern. So note the pattern of the sequence. What we have is a1 is equal to, well, this one here, notice that if this is the first term, notice how it goes from 3, 4, 5, 6, 7. So in other words, if that's the first term and it's positive, so what we'll have is, I'll write positive, then it's the first term plus 2. This one's going to be the second term plus 2. This one's the third term plus 2. And it keeps going on. This is going to be 5. Notice 5, in other words, 5 to the power of 1. And then this one is going to be, and then a2 is going to be, this one's going to be negative, and then we have a negative, then the second term is 2 plus 2. So 2 plus 2, notice the exact same 2 there. And then divided by, now it's 5 times 5. That's just 5 squared. And then the next one is, well, a 3. This is going to be positive now, so plus 3, this term, plus 2. Divide this by, then that's going to be 5 to the power of 3, because that's just 5 times 25 is that. So we already have 5, 3 like that. And then the last, one more term, let's get the fourth one. We have now a 4 equals to now a negative, and then it's going to be 4 plus 2. 4 plus 2. And then this is going to be, well, that's just going to be 125 times 5. Because notice if you times by 2, we get to 250. Times that by another 2, we'll get 500. So then we have 2 and 2, that's 4. And then plus 125, that's going to be 625. So in other words, we did multiply this by 5. So we have, this is going to be, that's 5 to the power of 3, add another 5. So at 5 to the power of 4, like that. And now I want to make a note. So note, what we have is, note, if we have negative 1 to the power of 1, this equals to, well, negative 1. But this starts at the first term. Thus, but the first term is a positive, not negative. So it's there. So thus, we start with negative 1 to the power of 0, which equals to 1, or equals positive 1. Or we could write this as negative 1, and then if we start with 1 like that, we'll have a 1 minus 1, which equals to a negative 1. 0 equals to 1. And we could also do a plus, that it doesn't matter, actually. We could even write that down, plus or minus. So this put a note as well here, plus or minus 1 works. So we'll have 1. And because, if you add a plus will be a 2, then it'll be an even number, and then that's just going to make it positive initially. So yeah, just put that there. It works like that as well. But we'll just stick with this one here. So thus, the pattern, thus, an is going to be equal to, well, negative 1, and then we'll just have this one, 1 minus 1, or n minus 1, because that's just for the first term, n minus 1. Then we have n plus 2. and then all divided by 5 to the power of, well, 1, 1, there's 2, 2, so n. Like that. And now let's look at another example on notation. Here is example 3, and it states here are some sequences that don't have a simple defining equation, and we're given A, where it's the sequence Pn, where Pn is the population of the world as of January 1 in the year n. So yeah, it's gonna not have a simple defining one. You could probably get one or fit a model to the population growth or decay. But if we, and then part B is if we let an be the digit in the nth decimal place of the number e, which is number e is 2.7182818, keeps going on, then an is a well-defined sequence whose first terms are 7182, yes, there's a 7182, 81, 82, 84, 45, etc. So that's defined based on the number e. So that's a sequence there. And also now, a very interesting one, the Fibonacci sequence Fn is defined recursively by the conditions, and recursively just means you're repeating over and over again. It's done by the conditions. F1 equals to 1, and then F2 equals to 1. And yeah, but I believe in computer science, modern computer science, they could also start with F1 equals to 0. And then F2 is equal to 1. But anyways, we'll just do the original. So then the next terms after that, so Fn is going to be Fn minus 1, so this one, plus the other term. So always the previous two terms. Fn minus 2, and this is for n is greater than or equal to 3. So yes, I'll be exploring more about this Fibonacci sequence later videos. And yeah, each term is the sum of the two preceding terms, so we could just easily write these terms down. So the first few terms are, so we have initially, we have the first term, F1 is 1, the second term, F2 is 1, and then the third term, we just add the previous two. So 1 plus 1 is going to be 2. So then we throw this over there. It's going to be 2, and then add these up. This is going to be, well, 3, and then throw this over there. That's going to be 3. Then likewise, this one's going to be 5, and then 5 plus 3 is going to be 8, and then 8 plus 5 is 13. 13 plus 8 is going to be 21, and then, well, so on, like that. Keeps going on and on. So very, very interesting. And yeah, this sequence arose when the 13th century Italian mathematician known as Fibonacci solved a problem concerning the breeding of rabbits. And I go over this problem in exercise 4 at the end of this video, as well as cover briefly on Fibonacci's life, so stay tuned for that further down below. And now let's go over the limit of a sequence. So a sequence such as the one in example 1a, where it's an equals n over n plus 1, this is right here, so 1a, n over n plus 1. You can see this number's right here, 1 over 2, 2 over 3, 3 over 4. You can see it's always going to be, well, less than 1 there. I'll show you further here. Yeah, this sequence, it can be pictured either by plotting its terms on a number line or by plotting its graph as in the figures below. But first, let's just write this out again. So if an equals to n over n plus 1, so then the sequence is going to be like this. We'll have 1 over 1 plus 1, the first term is 2, then 2 over 3, then 3 over 4, then 4 over 5, and it keeps going on and on until we get eventually we get something even like 100. Yeah, whoops, dot, and then 100 over 101 over 101, dot, 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 and then all the way it keeps going on and on, n plus 1. So in other words, the denominator is always 1 larger than the numerator. So in other words, it will never be greater than 1. So it's always going to be, it appears like it's approaching 1. Thus what we end up having is an infinity over an infinity plus 1. So in other words, it's approaching 1. Now if you were to draw this on a number line like this, what we have is initially 0, and I'll write this as an. So that's initially, there's the 0, but at the first term is 1/2. So let's say 1 is over here. Actually, I moved it around. Let's say we have 1 over there. So the first term, a1, is going to be at the half. This is a1. Then the second term is at a third. So that's going to be somewhere, let's say third would be somewhere around here. A2, this is 2/3, like that. So I'll just erase this part. Well, yeah, just assume it's there. So then the 3/4, now it's going to be at the 3/4 mark. So A3, and then the A4 is 4/5, and 4/5 is going to be somewhere around over here, A4. Actually, it's going to be a bit bigger than that. It's going to be somewhere around here, A4, and then A5 would be somewhere across like this. And as you can see, it just keeps getting, well, closer and closer and closer and closer and closer, like this. And it keeps getting closer and closer to this 1, and there's going to be a wall here that never gets close to it. So it keeps getting closer and closer to 1. So yes, it's like forced upon this wall there, right there. So yeah, it appears to be approaching that limit. And in fact, I'll prove it is further down in this video. And also now, if you were to graph this in a different way like this, let's say we had n, this is an, just in a graph form, so this is 0, and let's say we had, this is 1, so there's the value 1, let's just draw this line across, let's draw this line across, 1, yeah, so the first term is going to be like this is just going to be 1, the first term is at the half. So there is at the point right here. The second term is 2. That's going to be at the 2/3, be somewhere across here. Then we have the 3, 4, 5, 6, 7, and then it keeps going on. There's a 3 is going to be at the 5th. There's the 4th, and then there's the 5th, there's the 6th, 7th, and the 7th is this height is going to be, well, A7. Which equals to 7/8. So just 1 more than the numerator, 7/8, and it keeps getting closer and closer. So yeah, it's just keeps getting closer and closer to that line there. And now note that since the sequence is a function whose domain is the set of positive integers, as you can see all these positive integers, its graph consists of isolated points with the following coordinates as I drew above here. This one's going to be 1, 1/2. So there's 1, 1/2 is at that point. And then they're going to consist of something like this, A1, A1, and then we'll have 2, A2, and then 3, A4, I mean 3, A3. And so on, and then we have dot dot dot. Then we have n, a n, like that, dot dot dot. Keeps going on and on. Yeah. Now from the above figures, it appears that the terms of the sequence a n equals n/n+1 are approaching 1 as n becomes large. In fact, the difference, if we were to write 1 minus that sequence, 1 minus a n, which equals to 1 minus n/n+1. And now what we'll do is just multiply this top and bottom by n+1. This equals to, well, n+1 over n+1 minus n. So this is, I just multiplied that by n+1 on top and bottom, so same common denominator. This cancels, this cancels. This equals to, well, 1 over n+1. In other words, this value right here, this is pretty much approaching 1 over infinity as n approaches infinity. So when this gets super large, in other words, it's approaching 0. Yeah, so basically any number you put in, you can put bigger and bigger, it's just going to get smaller and smaller. So then basically that difference, the difference between the sequence can be made as small as we like by indicating n sufficiently large. In other words, that difference is going to be getting smaller and smaller. It's going to be getting smaller and smaller. And yeah, smaller and smaller, closer to that 1. So there's 0 difference eventually. Yeah, as the limit goes to infinity. So we indicate this by writing the limit as n approaches infinity of n over n+1 equals to 1. And in general, the notation, so this notation, limit as n approaches infinity of an equals to L, limit. Yeah, so this notation means that the terms of the sequence an approach L as n becomes large. And notice that the following definition of a limit of a sequence is very similar to the definition of a limit of a function at infinity, which was given in my earlier videos. So recall first the definition for limits at infinity from my earlier videos for a regular function. So let f be a function defined on some interval a to infinity, then the limit as x approaches infinity of f of x equals L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large, getting larger and larger, and then the value gets closer and closer to L. So this is very similar to the following definition for the limit of a sequence. Definition 1. A sequence AN has a limit L, and we write limit as n approaches infinity of AN equals to L, or you could write this as AN approaches L as n approaches infinity. And this limit, we have this limit if we can make the terms AN as close to L as we like by taking n sufficiently large, and again, pretty much identical to the earlier definition for regular functions, and also for defining convergence. So if limit as n approaches infinity AN exists, we say the sequences converge or is convergent. Otherwise, we say the sequence diverges or is divergent if it does not converge, or if the limit does not exist. And the graphs below shows two sequences that have a limit L, and you could graph it like this. This is one of them. Let's draw it like this. This is n, this is AN, this is 0, and let's say we have a limit L like this. Then what we have is to separate each points. So remember, it's integers, and here is one way of writing it. So this one would have a limit, would look like this. So as you see, this one's approaching it. It goes up above and comes back down, approaching it, and it's approaching that limit L. So that's one way. Another form is you can even have it like this. It's still going to be the limit AN, and then we have the same L, like that. Let's try it even further. So what we can have is, again, similar, but let's say we have something like this. It goes up and up. So this one, it could oscillate. And yeah, as you can see, this one, it's just oscillating around this. Oops, I'll draw this a bit better. It's going to be something like this. Whoops, yeah. Yeah, so you see this one is getting closer and closer to this way. So this is getting closer and closer, but it's oscillating around the limit, but it's still getting closer and closer, and both of these have limits L. So both have limit as n approaches infinity of AN equals to L. Yeah, so now let's look at a more precise version of the above definition, and it is as follows. So the precise definition would be definition 2. A sequence AN has the limit L, and we write, it'd be the same, initially same thing. So limit as n approaches infinity of AN equals to L, or AN goes to L as n approaches infinity. And this is if for every number epsilon greater than 0, there is a corresponding integer n, such that if n is greater than this integer n, then the difference, or the absolute value of the difference AN minus L from the limit, is less than epsilon. So in other words, it doesn't matter what this number is. You can make it infinitely small, but as long as it's greater than 0, then if there is an integer n such that AN is minus L is less than that, that means that, yeah, we have the limit. It's getting closer and closer to it. So yeah, make sure to watch my earlier videos on precise definition of just regular functions to get head wrapped around this format. But it's basically being more rigorous in the mathematical approach to defining how these limits are. Instead of saying sufficiently large, you go into infinity, you set exact parameters. So if you have any number greater than 0, you're always going to have this scenario. And I'll illustrate this both with a number line and with a graph. So the precise definition of a sequence is illustrated by the figure below, in which the terms A1, A2, A3 are plotted on a number line. No matter how small an interval L minus epsilon or L plus epsilon is chosen, from there to there exists an n such that all terms of the sequence a n plus 1 onward must lie in that interval. Yeah, so what this means is that we could, if we draw a number line like this, So let's say these values are a(n), this is at 0, and let's say our a1 is somewhere over here. But let's say we have a limit right across here. This limit exists and it's at L. So if it exists by the precise definition, let's just put some bunch of other plots. Let's say it oscillates, the values of a(n) oscillate about it. This goes a2, say it goes to a3 over here, and it jumps to a4 over here, and let's say it goes to a5. Then it goes to a6, like that. Let's say it jumps to a7, like this. But then let's say it jumps to a8 over here. But eventually, as you get more and more, it's going to go converge towards this L. So if it converges, then what we have to have is, we have to have a value here. We have to have I'll put a value like this. Or an interval. This is going to be from L. This is L minus epsilon, and this one here is L plus epsilon. So we have this interval that always exists where the distance from here to L is just epsilon. This difference is just epsilon. So remember, the absolute value of a(n) minus L has to be less than epsilon. Yeah, so if there's a limit, then there's always going to be a number, no matter how small, and that's epsilon as long as greater than 0, such that any any a(n) bigger than the number n, like that. For example, here, let's say we have this one here is a capital N plus 1, and this one, let's say here is a capital N plus 2. So in other words, we have, right here, so always the case, this is always the case, for, this is a(n) is going to be greater than, actually, not n, doesn't need to be greater. It's always the case for n is greater than capital N. For example, in this case right here, that is just, well, n equals to n plus 1, which is, well, greater than n. And same for this n plus 2. So for example, if we make this even smaller, then we always need to have this case valid. So we still need to have a number n such that anything greater, so even if I have n plus 2, n plus 99 or whatever, as long as it gets smaller and smaller. Yeah, so for example, I'll draw this in red. Let's say we had an even smaller epsilon, so we could even have a smaller one smaller than these ones. Then what we'll have is something like this in red, epsilon. This one right here is epsilon. So then it's going to be across here, like that. Then all that will happen is, well, we have a new n, a new capital N. So we're going to have new values here, where this is going to be, well, a n plus 1, and this is also going to be a n plus 2. And these are going to be new values of a, n, and epsilon. So this is smaller, but this capital N is going to be smaller as well. They're not the same ones. As you can see, so you could always repeat this. That means the limit exists and it's getting closer and closer. And now note that the above figure shows that any number epsilon greater than 0 will always have a corresponding n less than n right here. So you're always going to have, so this one over here corresponds to that n. Yeah, so these intervals correspond to it, so anything greater than it will be fit inside here. So you could even have a n out here, but remember it's an integer, so it could be somewhere between. But anyways, so let's go further. So another illustration of this precise definition is given in the figure below, which is also pretty interesting illustration. Helps illustrate this this very rigorous view of the limits. We're using precise laws, but it's very mathematically interesting. So we have n all the way to an, and then we have 0, and let's say we have the limit L. So the limit exists. The limit is L. And let's say we have the interval, so across here, this is going to be right here, this is the line y equals to L plus epsilon. So L plus epsilon, this is going to be, this difference is just epsilon, like that. Then we have the bottom part of it, this is going to be epsilon as well. And this is this line is y equals L minus epsilon. So then if the limit exists, then we always have to have, let's say we have the integers 1, 2, 3, and it goes to 4, and it keeps going on and on. Let's say we have n is right over here. Say this is n. So somewhere across here, somewhere across there, needs to be in between there. So let's say this goes up like this goes up, and then this goes up. Okay, let's just say it keeps going up. and then it keeps, then it starts going down, and then this is the n corresponds to this, so that anything greater than this n is going to be inside this interval. So then it goes down and down, like this. So see what I did there. So there's the n. So this corresponds to it, and this is something like this. This n would go, let's say it goes all the way across to this one here. Let's say it goes across this point, but then greater than it's going to be within this interval. So then this corresponds to the n. So this is the corresponds. Or better yet, put an arrow there, right, corresponds, and then put this arrow across there. And this is for, well, anything to the right of this. In other words, n is greater than n on this side here. And then if you were to draw this in red for an even smaller one, so let's just draw a smaller one as in a number line, like that, a smaller interval, and this is going to be, well, a new interval, epsilon there, even smaller, then we're just going to have a different corresponding n. So in this case, this one's going to be the corresponding one, because greater than it's going to be over there. So that's going to be the corresponding one, like that. This is going to be n, like that. And then this corresponds, let's put it right here, corresponds. So this corresponds to this one over there, or these correspond to each other. Flip the arrow around. Yeah, so thus shrinking the above intervals, i.e. making epsilon smaller, just moves the corresponding n further to the right towards n over there, just going over further to the right there. And the points on the graph an must lie between the horizontal lines y equals l plus epsilon and y equals l minus epsilon if n is greater than n, as I just illustrated there. This is a very good illustration. So the picture must be valid no matter how small epsilon is chosen, but usually a smaller epsilon requires a larger n. It's very interesting. So now if you compare the precise definition with that in my earlier video on the precise definition of limits at infinity, just for general functions, you will see that the only difference between the two is that n is required to be an integer. So here's the definition: let f be a function defined on some interval a to infinity, then limit as x approaches infinity of f of x equals L, means that for every epsilon greater than 0 there is a corresponding n such that if x is greater than n, then f of x is less than L minus epsilon. So this is the exact same thing. Instead of corresponding number, we have corresponding integer, as here, corresponding integer, like that. And we replace n with x, or x with n. So thus we have the following theorem, and which is illustrated below. So this is exactly the same thing. We just make it now for integers, a number integer instead of just any number. So theorem 1. And theorem 1 states if limit as x, if limit as x approaches infinity of f of x is equal to L and f of n is equal to an, equals to an when, let's put the when down here, when n is an integer. So in other words, if the function and the sequence are the exact same, but now you're just dealing with integers as opposed to just any real number, then what we have is the limit is also equal. So then the limit as well is the same. So n approaches infinity of f of n, which is just an, of an is equal to L. So the limits are the same. If it's the same function, again, it's exactly the same definition. We just made it integer instead of a number. Instead of any number. So if you were to graph this out, what this means is this theorem just represents pretty obvious. So let's say we have, I'll put x or n. So this horizontal axis is x or n, and the y and the vertical one is y or an. So a sequence or the function of the sequence. So then we have L like this. Let's draw a better straight line. This is L. And let's say we have 0 like this. This is the integer 1, this is integer 2, this is integer 3, and integer 4. So for the function, what we'll have is, say the limit exists and it goes down like this. So this is the function. Draw this a bit better. Like that. So this one right here is y equals f of x. And now for the sequence is the function, but in only in integer form. So we just draw the dots there. This is all it is. So there's the fourth, and then it just keeps going on like this. And let's say it's something like this. Yeah, so you could see that it just gets closer and closer, like that. So then these points are the AN, which equals to f of n, as above there. So it's exactly the same thing. So all we do is plot the integers on the function, and hence the limits are the same. Yeah, so now in particular, let's take a look at the following limit. And this is I've covered in my earlier videos. So let's say a limit as x approaches infinity of 1 over xr, where r is greater than 0 and is a rational number. Rational number. So remember that if it's a rational number, this just means that, well, i.e. 2 over 5, for example, we have 3 or 4, etc., and it's all greater than 0, so etc. In other words, can be written as a fraction of integers. For example, 2 and 5 of integers, like that. Circle this, like that. Then what we have here is for the limit, so then just now we can apply limit laws. Limit as x approaches infinity of 1 over xr, this equals to, recall that using limit laws, this just equals to the limit as x approaches infinity of 1 over x, and then take this out to the r, and then use further limit laws. This just equals to limit as x approaches infinity, put a bracket around this whole thing. This is going to be 1 over x all over r. So in other words, this is just a limit of 1 over x, which is just equal to, well, 0. This goes to 1 over infinity, which is equal to 0, or approaching 0. The inside there. So we have 0 power of r, which is equals to 0. So in other words, the limit is equal to 0. Yeah, so we could write this in sequence form, and we get, well, limit as n approaches infinity of 1 over n, instead of x, n to the r. So instead of x, we replace it, n to the r, and this equals to, well, 0, because that one is equal to 0. And this is if, let's write if if r is greater than 0. Again, is a rational number for this case. Rational number. And now let's look at infinite limits of sequences at infinity. So if an becomes large as n becomes large, we use the notation, and we use this one, limit as n approaches infinity of an, this equals to infinity. And yeah, this just means that the limit's going to infinity. This is diverging to infinity, as I'll explain, as n goes infinity. So the following precise definition is similar, put a space here, similar to my earlier video's definition. A definition for infinite limits at infinity, and let's go over that. This is going to be definition 3. So definition 3 states the limit n approaches infinity of an is equal to infinity. Yeah, this means that for every positive number m, there is an integer n such that an is going to be greater than this positive number m whenever n is greater than n. So very similar, but instead of an interval, now we just have a greater than a number because it's going to infinity. Yeah, so thus for any number m, regardless of how large it is, the sequence has a point that is larger, i.e. always increasing. And you can always determine that where n is greater than this specific number n. And compare with my earlier video's definition for infinite limits at infinity. This one stated, let f be a function defined on some interval a at infinity, then the limit as x approaches infinity of f of x equals to infinity. Means that for every positive number m, there is a corresponding positive number n such that if x is greater than n, then f of x is greater than m. It's the same thing as whenever you could use if then. It's exactly the same thing. So graphically, both these definitions are illustrated below, and I've just made it for f of n equals to an, where again it's integer, where n equals to integer greater than 0, positive integer. So just to illustrate both at the exact same time, let's write it that way. So we have, let's say we have x and we have n, we have y and we have a n like this, and let's say we have a graph that goes like this. Is it 0? It goes up like that. So we have y equals to f of x like that, and it's going to infinity. And let's say, so then if it's going to infinity, then there's always a number m over here such that this number m corresponds to a number n, in this case an integer for our other case. So, but right now it's going to be a number n, so that's all we do is replace a positive number with positive integer. So there, integer n, like that, such that we have f of x is greater than m. So we could, for n is greater than, if x is greater than n. So for example, to the right here, we have x is greater than n. Or, I'll do the integer ones after. So if x is greater than n, for example, we'll always get a point like this right here, where this is x is greater than n, and this is right here. And it corresponds to a number all the way across here, where f of x now is greater than m. So this height is greater than this one, and this one is to the right when x is greater to the right of n. And likewise for sequence, let's say 1, 2, 3, 4, that corresponds to the function. So we have this, 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 and it's the exact same thing but in sequence form. So say it keeps going up, say it keeps going up, and then we have, so we have this corresponding stuff like that. So if there is a number m corresponding to n like this, and or integer like that, doesn't need to be, actually it should be on it actually, because it says it's corresponding to an integer that, say it's connected right on it, then it goes over here. Actually, to illustrate this a bit better, this needs to be on the integer because that's integer n, but this doesn't need to be on it. It could be somewhere across here. It could be somewhere across there, for example. It could be there or below, or it doesn't matter. Any number you pick, you're always going to have an integer where when you get bigger than it, for example, this one there is going to be bigger. So for example, so that's integer. This one right here is, well, that's an n that's bigger than this one. N is bigger than capital N. So to the right we have x is greater than n and n is greater than n. And then this point right here, this one here is, well, all the way across, this is just n is greater than n, and this one here is an is greater than m, where again these points are just an. And in our case equals to fn. For this illustration, just leave it like that. So yes, very, very interesting stuff. So that's all it means. So at any point, if it's actually increasing, you could always find any number, however large it is, you'll find a corresponding a number or integer n, such that the function will be bigger than it when x or n is bigger than capital N. So thus again, this graph needs to be valid no matter how large n is chosen. And now it's when make another note. Note if we have the limit, so if the limit is going to infinity, so if, just for a notation, if limit as n approaches infinity of an is equal to infinity, then an, the sequence is divergent, but in a special way when we say that n diverges to infinity, or using that symbol like that, the infinite 8 symbol, horizontal 8. So that's just terminology. So now limit laws for sequences. The limit laws given in my earlier videos also hold up for sequences, and their proofs are similar, i.e. we essentially just replace the functions with sequences as per Theorem 1, because all we are changing is instead of dealing with all numbers, we're dealing with integers only. So we can just write these down, and they're exactly the same. So if the sequences an and bn are convergent sequences, that is, they have limits and c is a constant, then we have the following limit laws. So we have limit as n approaches infinity of the summation, so an plus bn. This just equals to limit as n approaches infinity of an, and then plus the limit as n approaches infinity of bn. So we can separate those out, and even if it's subtraction, we could add the same thing. Let's put a negative here. So plus or minus an, bn, it's going to be the same thing. We just separate the limits plus or minus like that. Just to save time, just put a plus or minus. So now if we have a constant now, so limit as n approaches infinity of c times an, this just equals to, we'll take the constant out. So c times limit as n approaches infinity of an. And also, side note here, limit as n approaches infinity of c, the constant just s equals to c. So yes, so this is the same thing as the multiplication one, but the limit is c. So let's do the multiplication now. Limit as n approaches infinity of an bn, this equals to limit as n approaches infinity of an, now times this by limit as n approaches infinity of bn. So we just multiply the limits together. And likewise for division, so if we have limit as n approaches infinity of an, like this, an over bn, this equals to the limit as n approaches infinity of an over limit as n approaches infinity of bn. And this is if bn is not equal to 0, otherwise we'll have undefined, well, divided by 0 goes to infinity, or can go to infinity. So we can't have that. And now the last one is a power rule one, so limit as n, this one I went over for the just general function in earlier example. So limit as n approaches infinity of an p, this equals to, well, we could take this all out. So we take this whole p out, so we'll have limit as n approaches infinity of an of p like this. And this is if p is greater than 0, because if it's less, we're going to have some inverted scenario, and where an is greater than 0. Yeah, so if it's less, we'll have a fraction and so on. So we will not be dealing with that, and well, if we do, we need to manipulate the function a bit more. So this one is for p is greater than 0 and a. Alright, so now let's move forward, and now let's look at the squeeze theorem for sequences. And basically the squeeze theorem can also be adapted for sequences as follows. First, recall the general squeeze theorem for just general functions. Squeeze theorem: if f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a, and the limit of f of x as x approaches a is equal to the limit as x approaches a of h of x is equal to L. So if this limit is L, this is L, then this gets squeezed, and hence this becomes the limit as x approaches a of g of x is also equal to L. And basically an illustration of this is shown below here, just illustrated to recap on the squeeze theorem. So if this is x, this is y, and let's say we have, here is a, and let's say we have L, so this goes up across here, and L is right across there, like that. Yeah, to illustrate this, let's draw first h of x. Let's say it's the larger one, so it's always greater than g and f. So, but its limit is L, so this is the L, so it goes over to here. So let's say we have a function like this. This is h, and it goes across there, and it just goes around like this. This is h of x. And now let's say we have f of x. F of x is always less than h of x, or f of x. I mean g of x. So f of x is always less than h of x, or and h of x when x is near a. Let's just say it's less than for pretty much everywhere. Or actually, let's illustrate. It doesn't need to be less everywhere, just near a. So let's like that. And this is f of x, like that. Like this. Alright, so if we have something like this where both the limits are L of f of x and h of x, then g of x, if it's always going to be less than, well, in between h of x and f of x, near x equals a, let's say it's something like this. So even if it overlaps like this, as long as it's near, becomes like that, yeah. So if it's near it, it's going to be in between it. So in other words, this gets squeezed. So this one here, we could think of it as not near a. But anyways, so what we have here is, this is our f of x, and this gets squeezed inside, so thus the limit is also going to be, well, the same, L. So this gets squeezed inside, like that. Alright, so now, sequences we can, or thus for sequences we can write the squeeze theorem as follows and basically adapt the squeeze theorem to the sequences theorem. So squeeze theorem for sequences, what we'll have is if, so instead of the functions we have, if we have the sequence an is always less than or equal to bn, and this is where bn is less than or equal to cn, for we have n is greater than or equal to n0. Yeah, so for a specific point, if it's always going to be, if an is less than bn and less than cn for a specific value here above this n integer. And we have, and the limit as n approaches infinity of an, if this equals to the limit as n approaches infinity of cn, which this equals to L, then by squeeze theorem the bn gets squeezed inside. So then the limit as n approaches infinity of bn, the in-between function, is also equal to L, and it gets squeezed. And then graphically we can see this as follows. Remember, it goes to infinity. So let's say we have the y-axis like that. This is the, make this a bit better straight. This goes to n like that. So that's n. And then let's say we have L across here. This is L. And let's say we have a point right here. This is n0. So to the right of this is n greater than or equal to n0. Alright, so first let's draw the larger sequence at Cn. So let's say we have Cn like this. So this is our Cn, and then it's going down and down. It has a limit of L. Let's just say it keeps going down, and we're just drawing integers now as opposed to a straight line or continuous lines as in the above theorem. So we have that. And now let's say we have the an, which is the smaller sequence. Let's say it goes something like this, and it's just the opposite of this one. And it goes in like that. I'll just write this down. So this one here is our an, like that. So that's our an. Actually, right outside of this interval, write this over here. So that's our an. And now let's draw our bn, which is the middle one. So let's say, so greater than or equal to this one, and it has to be, let's say it is greater than equal, if for integer n is greater than or equal to n0, it's always in between there. So for example, let's say we have something like this. It goes like this, and then, or actually, let's just say it comes out from here. Say it goes from here, and then past this one here, this is n0. Actually, I quickly move that around, just make it a bit more to the right here so that we can draw one. Let's say it goes from here, then it goes above here, and then above this, now it's always in between. Let's say it goes something like this, and then it goes all the way above here, and let's say it just keeps alternating, and so on. So you can see here, yeah, whether it alternates or not, as long because it's always less than it for n is greater than n0 or n0, then notice how it gets squeezed inside. So we get over here, it gets squeezed. So we can write quote squeezed inside in between the two, larger and smaller sequences. And then this again is our bn. Alright, so moving forward now, another useful fact about limits of sequences is given by the following theorem, which I prove at the end of this video in exercise 2. But let's look at this theorem. This is theorem 2. So if we have the limit as n approaches infinity of an, if this equals to 0, then the limit of the, that's absolute value. If we just remove the absolute value, it's also equal to 0. Because remember, absolute value, all it means is it doesn't matter if it's alternating or not. This one, it just means it's alternating, but it's still, or it can alternate, it's still going to go to 0. So then this is going to be an equals to 0. Yeah, so now that brings us to another example. Let's look at example 4. This one states, find the limit of n over n plus 1 as n approaches infinity. And this is the one that we've been dealing with quite a bit earlier above. So what we'll notice first is, now that we know the limit definitions, we can solve this. So we know that, well, first of all, right here, if we plug an infinity inside this or large number, we're going to get an infinity over infinity, and this is not defined. So not defined. So, but we can do is, we could write limit as n approaches infinity as of n plus 1, and we can multiply the top and bottom by the, or divide it out by the highest power, which is n, right here. So 1 over n over 1 over n. So then this would cancel with there. So we get limit as n approaches infinity. We're going to have, well, 1. Then the bottom here is going to cancel. We're going to have 1 plus n over there. 1 divided by n over there. 1 plus 1 over n. Now this just equals 2. Well, now we can use the limit laws. This could just go now. This becomes, well, 1 over 1 plus limit as n approaches infinity. Just for completeness sake, put it like that. So in other words, this bottom part right here approaches, well, 1 over infinity, which approaches 0. So put that like that. This approaches 0. Yeah, so it's approaching 0 there, so we get a 1 over 1 plus 0. In other words, we get a 1. And we just proved it. And now note that this is the same limit we looked at earlier in this video, as I stated, but this time evaluated directly to prove that it is indeed equal to 1, instead of just doing the indirect methods before. Nonetheless, let's go further and look at example 5 right now. When this one says calculate limit as n approaches infinity of ln n over n. So first thing to note again is, well, ln of infinity is infinity, and divided by infinity, again we have an infinity over infinity. This is not defined, and it isn't written in a simple way like the one above here that we could just divide by the highest power on top and bottom. But so we can look at L'Hopital's rule. Yeah, so we can look at L'Hopital's rule, but we can't apply directly. So note, we can't apply L'Hopital's rule directly since it applies to functions of a real variable and not to sequences, but we can do a workaround and then apply Theorem 1 relating the limits of functions to sequences. So remember Theorem 1, also recall L'Hopital's rule is just the, if you have an undefined like this, we could take the limit of the derivatives of the top and bottom, and they should, and they are the same as the derivative of the regular functions. So let's just write this as a function instead of dealing with sequences, because L'Hopital's rule is not defined for sequences. It's defined for real variables and not integers. But nonetheless, we can just do a workaround. So limit as x approaches, so move that as a function, x approaches infinity of ln x over x. Now applying L'Hopital's rule, this equals to limit as x approaches infinity of the derivative. So ln x over dx, d ln x over dx, and then d over dx of x, so the derivative of top and bottom. And now if we take the derivative, recall the derivative of ln x is just 1 over x, and the derivative of x is just 1. So we just get, so we get a 1 over x. So let's write this limit down. So this becomes 1 over x over 1. So in other words, we get, well, just 1 over x. So then if you apply infinity over, so then this becomes, again, a 1 over infinity approaches 0. So this becomes 0, like that. Yeah, so thus by Theorem 1, what we end up having is just Theorem 1, because that's just a function, and then we just convert it into a sequence. The limits are the same. So limit as n approaches infinity of ln n over n equals to, it just equals to the limit as x approaches infinity of ln x over x. So this is a real function, that's a sequence. And this both equal to 0 because this equals to 0. So yes, very interesting. Yes, so now let's look at another example, example 6, and it states determine whether the sequence an equals minus 1 to the power of n is convergent or divergent. So, well, first thing we should note is, well, we could write the sequence out, an is equal to, and write all the terms. You could see that it's going to be alternating. So when n is 1, that's going to be the first term, so negative 1 to the power of 1 is just negative 1. Negative 1 to the power of 2 is just, well, positive 1. So we end up getting a negative 1, 1, and then the 3 is odd, so it's going to be negative. Power of 4 is even, so we get a positive. So again, it just goes like that, and it keeps going on, and so on. So it just alternates between 1 and negative 1. So if you were to graph this out, what you end up having is something looks like this. This is n, this is an, and we have a 1, and we have a negative 1 across here. So for 1, we have negative 1. For 2, we have 1, positive 1. And for 3, we have negative 1. And then for 4, we have positive 1 across here, and then as so on, so forth. Keeps going on and on. We just get like this and like that. And last one like this. So there is no convergence. Yeah, so since the terms oscillate between 1 and negative 1 infinitely often, an does not approach any number. So maybe put a space there. Actually remove that. So thus what we have is a limit as n approaches infinity of negative 1, and this does not exist. There's no limit. Does not exist. Like that. And the sequence, right here, negative 1, n is divergent. Alright, so now let's look at another example, and that's example 7. That's this right here, and it states evaluate the limit as n approaches infinity of negative 1 to the power of n. I'm in a negative 1 bracket, power of n, and then divided by n if it exists. Remember, this is alternating between negative and positive, but what we should note is, note what happens when we take the limit of the absolute value of that sequence. Limit as n approaches infinity of the absolute value of negative 1 n over n, and then this equals 2. Well, this is going to be always positive, so in other words, it's not going to alternate from negative 1 to 1, it's just going to be 1. And the bottom is going to be, well, always positive anyways, because it's n is positive integer. So it's going to be negative infinity, like this, limit as n approaches infinity of 1 over n. And this one we already know, this 1 over infinity approaches 0. So we already know that, so thus we can just apply theorem 2. So thus, from theorem 2, we have, and if you just scroll up to theorem 2, remember that's just an absolute value. If it equals to 0, then the non-absolute value is also 0. So here's theorem 2. If limit of an of the absolute value of an as n approaches 0 is equal to 0, then the limit as n approaches infinity of an is also equal to 0. So yes. Yeah, so thus, let's just scroll down here. Thus what we have is the limit without the absolute value sign is also equal to 0. So limit as n approaches infinity of negative 1 power of n over n is equal to 0. So yes, very good use of that theorem, which again I'll prove at the end of this chapter, or this section, in exercise 2, I believe. And now this can also be seen graphically, this sequence, and we can see that by, let's just put a graph like this. If this is n, this is an, and let's say it goes from, well, we know that if we plug in 1 inside here, we're going to have a negative 1, and then divided by 1. That's going to be negative 1. So we're going to start off at the bottom over here. Yeah, just move this up a bit. So this is negative 1 is where we start. That's at 1. At 1, we're going to have it over here. So that is going to be negative 1 there. And then at 2, well, we're going to have, 2, if we scroll up here, it's going to be negative 1 power of 2 is 1, and then divided by 2. So we'll have 1/2. So this is 1. So we'll have 1/2 over there. That's going to be right over there. And then there's the 3. 3 is going to be, well, a third, but it's going to be negative, and it's going to go over there. And then there's the 4. A 4 is going to be a fourth, and that's going to be a positive because it's even, so it goes somewhere over there. And then as you can see, we can keep going on and on. And it just gets smaller and smaller. This will be over here, this will be over there, this will be across there. And as you see, the limit is going to get, well, smaller and smaller, approach 0. Yeah, now we're going to look at another theorem. So the following theorem says that if we apply a continuous function to the terms of a convergent sequence, the result is also convergent. And what I mean by this, applying it, what we'll do is if we have a convergent sequence, let's say limit as n approaching infinity of so n approaching infinity of an, if this equals to L, and we're also given that the function is continuous at L, so the limit of the function as n approaches whatever value is going to be L, then what we also have is the limit when we apply this function to the sequence. In other words, the limit as n approaches infinity of f of an, so applying that function to it, is just going to be, well, f of L. This is continuous, so we just plug that L inside. And yeah, I proved this theorem later in this video in exercise 3, so stay tuned. So now let's look at another example that uses theorem 3, that's example 8. It states find limit as n approaches infinity of sine of pi over n. Well, first thing we note is it's a function of a sequence, so we know that, note that the limit of the sequence, so n approaches infinity of pi over n, this just equals to, well, that's a 0. That's just going to be a number divided by n, and this goes to infinity at the bottom, so number divided by infinity goes towards 0. So that's equals to 0. So it's equal to 0. Yeah, it's equal to 0. In other words, it equals to a limit, and that is 0. And since the sine function is continuous at 0, it's actually continuous everywhere, then theorem 3 enables us to write limit as n approaches infinity of this sine function, sine pi over n. This is going to be equal to, well, sine of, we could take this entire sine out, so it's going to be applying the function to that limit now. This is going to be sine of limit as n approaches infinity of this inside sequence, like that, which equals to, well, that's 0 inside, so sine of 0, and we all know sine of 0, recall, is just 0. And now let's look at another example, and that's example 9, and here we're asked to discuss the convergence of the sequence, and we have an equals to n factorial divided by n to the power of n, and where n factorial, recall, is just 1 times 2 times 3 times 4 times etc. keeps going all the way until n. So first thing to note, as always here when we're dealing with infinite sequences, look at what happens when you put large number in the top and bottom, the numerator denominator. Well, we have right here, this is going to be infinity, because as you put larger and larger number, infinity factorial is going to be infinity, and we're going to have an infinity to the power of infinity. In other words, this is all going to, infinity factorial, it's going to be infinity, infinity to the power of infinity can be an infinity, and then basically we are, well, not defined. Not defined, so we have to find a way to solve this limit. And now note also that we can't use L'Hopital's rule because the corresponding function x factorial is not defined when x is not an integer. Remember, recall L'Hopital's rule is just for a function of all real numbers. And this one again is for integers. You can see this 1, 2, 3, 4, etc. So it's not defined for that. So let's instead let's write out a few terms to get a feeling for what happens to an as n gets large. So let's just write it out and see if we can find a pattern. So a1 is going to be equal to 1 factorial. Divide this by 1 to the power of 1. That is just, well, 1 over 1. And that is just, well, equals to 1. So that's obvious. So a2, this one's going to be, well, 2 factorial divided by 2 to the power of 2. So this is going to be equal to 1 times 2 over, this is going to be 2 times 2. And instead of writing it out, I'm just going to leave it like that. Let's just see a pattern. Because then when we have a3, notice what we have now is going to be 3 factorial over 3 to the power of 3, which equals to 3 times, or I'll put it 1 first. So 1 times 2 times 3 over 3 times 3 times 3. Then keep going on and on, dot, dot, dot. What we have for an now is going to equal to n factorial divided by n to the power of n, which equals to 1 times 2 times 3, and this is going to keep going on. 1, 2, 3, it keeps going on all the way, and this is going to be now n times n times n times, and then dot, 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 times n, like that. And now it appears from these expressions, as you notice here, that the terms are decreasing because the numerator, even though it's getting bigger, the denominator is getting exponentially bigger. You have this n times n times n, or this 3 times 3 times 3, and it's always going to be bigger and bigger than the top one. So it does appear it's decreasing and perhaps even approaching 0 as it gets to near infinity. So to confirm this, observe that for the nth term we can rewrite the expression as follows. So we could write this top part instead. We could write it as an equals 2, and then take out this 1 over n. So we have 1 over n times it by now. Just all we do is put in a bracket. So now we have 2 times 3 times, it keeps going on and on, times n, all the way. Then this is going to be divided by n times 1, 2, 3, 3 dots, just to make it consistent, like that. And now what we notice is, well, this is going to be 1 over n times, an equals to 1 over n times by this number. But this number, you can see that the denominator is bigger than the numerator. So in other words, this entire bracket is going to be less than or equal to 1. If n is equal to 1, then we just have 1 over 1. So yeah, notice, as I just stated, notice that the expression in parentheses is at most 1 because the numerator is less than or equal to the denominator. And so thus what we have is, we have an is going to be, well, first of all, it's greater than 0 because we're a positive integer, and there's no negative sign, so you're not going to be less than 0. And then what we have is now this is going to be less than or equal to, and it's 1 over an. And the reason is because, well, we're multiplying this 1 over an. This is i.e. 1 over n is going to times it by a number less than 1 or less than or equal to 1 is going to be less than or equal to an. So yes, that's what we have. And we also know from earlier, so I'll write and, we know that a over n approaches 0 as n approaches infinity. Just put infinity out there, you go 1 over infinity goes to 0. So thus what we have is, an, well, it gets squeezed. Notice this is just a squeeze theorem. So that's 0, so it's bigger than that, but it's less than this one, which is approaching 0. Thus an approaches 0 as n approaches infinity. And in other words, so by the squeeze theorem, or it's convergent. So by the squeeze theorem, and it converges, so it is convergent, not divergent. Squeeze theorem. So yes, fascinating stuff. I'll just box this out. Let's do a better box, like this. And there it goes. And now that we got to that example, we'll go through a quick segment on creating graphs of sequences, and then I'll show you how you can graph this particular sequence. So some computer algebra systems have special commands that enable us to create sequences and graph them directly. And with most graphing calculators, however, sequences can be graphed by using parametric equations. For instance, the sequence in example 9 can be graphed by entering the parametric equations. So recall parametric equations, we just add another parameter, so x equals to t, then we'll have y equals to t factorial. Divide this by t to the power of t. And then after setting it to parametric equations and then graphing in dot mode, starting with t equals 1 and setting the t step equal to 1, we can graph it, but I'm not sure which calculator my calculus book was referring to. This is from my calculus book, but the trusty Desmos graphing calculator always has a way to graph just about any function. Here I've set up how you can graph it in Desmos graphing calculator, and so we could write the function a of x equals to x factorial, divide this by x to the power of x. I've hidden this otherwise it will show the function around like that, and we'll use it as a function. Then what we could do is graph. This is going to be a parametric equation actually, but the way this way set up, you put n and then a bracket a of n, so there's the x, there's the y, but then you could set up a list here. So if you write n equals to bracket 1 comma dot 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 and then all the way to n, it shows a 100. No, then I have set up capital N equals to 100. So then we have a 100 element list, and all the step is just 1 2 3 4 all the way to 100. And as you can see, we have a sequence like this, and it converges right to 0 very quickly. And let's just click this and play around with this graph. Very fascinating stuff. Alright, so here's the graph. I'll just make this projector mode, so sticker. So notice what we have here. There it is. It converges. And again, if you change this one right here, whoops, let's change this back. So if you change this one to 10, notice then it just removes all of those over there. And then put another one there, and so on. And you could just hide the axis, remove the grid. Anyways, you can do a lot of other stuff there. So it's very fascinating stuff indeed. And if you click this, it shows that function. That's just the function. That's an interesting point over there. So anyways, that's fascinating stuff indeed, and you could hide these, and then let's see, we'll cover it and move it up, and it moves around. So anyways, that's pretty cool stuff. Play around with that calculator. Very fascinating stuff. So yes, the graph converges very quickly to 0 after about the 10th term from here. Hashtag nice. Alright, so now let's look at another example. This is example 10, and this one we're asked, for what values of r is the sequence r to the power of n convergent? So this one here is very interesting. I've actually covered this in my earlier videos, so I'll just put a recall. Yeah, recall that for setting this in function mode, limit as x approaches infinity of a to the x, this is equal to, I'll put this big like this actually, like that. This is equal to infinity if a is greater than 1. So if it's greater than 1, then you're going to have a power or a number to the power of infinity, which just keeps going, a larger power, it keeps getting bigger and bigger and bigger, so it approaches infinity. But this equals to 0 if we have a fraction that is, well, a, where it's less than 1, but greater than 0. So yeah, so recall that, well, for example, to illustrate this point, for example, if you have a 1 to the 1/2 or 0.5, that's in between there, then to the power of infinity, this becomes, well, 1 over 2 to the infinity, and then this becomes, well, 1 over infinity, and this goes to 0, and so on. Just put a little illustration there. Yeah, so thus we can replace a with r and x with n as with theorem 1. So because if it's the same function, but then in integer / sequence mode, it'd be the same thing. So we'll have limit as n approaches infinity of, instead of a, we'll write, I'll just write r to know that we're dealing with a different one. And also because we're dealing with r there, my bad. So we have r there, r to the power of n, and now this, is equal to, if we have to put an equal sign there, so this equals to, and then this opens up, and then we have infinity if r is greater than 1, and it's 0 if r is a fraction. Is a 0 less than r less than 1. And since we're asked what values of r is this sequence convergent, well, 0 is convergent, so we have this value right now, where r is between 0 and 1. And now let's consider the trivial case r equals to 1. Let's put this in another space. So r equals 1 and r equals to 0. So for r equals to 1, what we have is limit as n approaches infinity of, well, 1 to the n, that is just, well, 1. So that is convergent as well, so we have a value there. And now for the other obvious or trivial or obvious one, for r equals to 0, what we get is the limit as n approaches infinity of 0 to the n. Now, well, that's still just 0. And that's also convergent. So we have this, and this one. And now let's look at the other case where it's a fraction, but it's a fraction, but on the negative side. So if we have r as a fraction or a decimal place, or just a number, it doesn't need to be a fraction. It's going to be less than 0, but greater than -1. So it doesn't need to be a fraction. I just want to clarify that. But you know what I mean, or you should. So if we have this case, then recall again that this just means that the absolute value is, well, greater than 0 and less than 1. So that's just absolute value. So we could just apply theorem 2. So thus limit as n approaches infinity. So n approaches infinity of absolute value of r to the n is equal to the limit as, well, n approaches infinity, and this is the same thing as putting r absolute value to the n like that. So these are the same things. It's always going to be positive, so this will literally just act exactly as over here. So thus this one is going to equal to, well, 0. This is the same thing as this one above here. This part right here where 0 is between where r is between 0 and 1. So thus this is convergent for the values. Or I'll not circle this one, I'll leave the circling for applying the theorem. So thus, by theorem 2, since the absolute value of the sequence is 0, or the limit is 0, so too is the sequence itself. So thus, limit as n approaches infinity of r to the n is equal to 0, like that. And now the last one is if r, so if, I'll put a better line, oops. So if r is less than or equal to -1, well then this one is obviously going to be divergent. Then Rn is divergent. And this is as in example 6 that I covered earlier, as in example 6. And we can scroll all the way up there to example 6 just to recap on it. So there's example 6 right here. Remember that these ones, this is for r is -1. Notice this just goes back and forth. So -1, -1, positive 1, -1, positive 1. But when this is less than that, for example, if it's 2, if it's -2, then we're going to have just, all it's going to go is further up. So -2 to the power of 1 is going to be -2. And then -2 to the power of 2, that's going to be, well, positive 4. So it's going to be bigger and bigger. It's going to actually go back and forth, but even farther out to infinity. So that's also divergent. So yes, let's scroll back there. And now to illustrate all these points, I'll just graph these out. So the following graphs plot various values of r. So let's look at where r is greater than 0. So for it's positive. So for r is greater than 0, what we end up having is, draw this box better. Yeah, then what we have is, let's just graph this out like this. This is going to be n, this is a n, like that. And let's graph the first point, r is 1. So r is 1, well we know that when r is 1, it's all the values are just 1. Scroll up here, this one a n is just equal to 1. So then we have just 1. Like that. Any point we go is just going to be equals to 1. Yeah, just put those there, just fix up the axis. So this is going to be 1, 1, 1, and this one is for r equals to 1. And the next one is when r is greater than 1, well that's over here goes to infinity. So we will just have a point here. So if it's greater, it's going to be somewhere like this, and it's going to get bigger and bigger. For example, if it's 2, 2 to the power of 1 is just 2, 2 to the power of 2 is 4, 2 to the power of 3 is going to be 8, and so on. So it just gets bigger, and yeah, exponentially bigger. Let's draw this a bit better there, just to fit in this graph. So this all the way here, r is greater than 1. And then lastly, for this one, we have when r is between 0 and 1, this goes to 0. So yes, as you see here, 1/2, and then it just gets bigger and bigger, bigger. So then we'll have starting here, draw this in blue, and it just gets smaller and smaller, like that. And this one is r is this is r is between 1 and greater than 0. And now let's look at the case where r is less than 0. So for r less than 0, and we already know what the case. Yes, so alright, this here we already know the case for r equals 0. That is just 0, as I showed above here. So for r equals 0, that's a 0. That's just a point on here. This is r equals to 0, and then we'll have a point everywhere actually. R equals 0, like that, and so on and so on. So we just ignore those. So yeah, that's just a trivial one. So is r equals to 1. Yeah, but anyways, let's graph for r is less than 0. So actually, if we have these ones all the way there, let's just add this for greater than or equal to 0, because it's equal to 0 there. Yeah, so now let's graph for r is less than 0. So this one, because it's less than 0, it's going to be alternating across the axis. So we'll make it in between this x-axis like that. This is the n, this is a n, and then let's draw the one we know, the one we solved earlier. This is 1, this is -1. So for r equals to 1, r is so negative, r equals -1. So -1 to the power of 1 is going to be, well, -1. -1 to the power of 2 is going to be positive 1, and then as you can see, it just keeps going, alternating across, and it's divergent. And it goes down like this. And then lastly here, and this is at r equals to -1. And then the next one we'll draw as well when r is less than -1. Remember, that is just divergent, and this is just alternating, but even further. So for example, -2, it's going to be -2 to the power of 2 is going to be, well, the power of 1 is going to be -2. -2 to the power of 2, that's going to be positive 4, etc. So it just gets bigger and bigger. So I'll just draw something like this, goes there, and then it alternates across here, and it's getting bigger and bigger, like that. And this one here is r is less than -1. And then lastly, again, as theorem 2 showed, when r is between -1 and 0, that also goes to 0. So then what we'll have is, so if it's a fraction, for example, the -1/2, the power of 1, that's going to be still -1/2, so it's going to be negative, and it goes to the positive, so it's going to get smaller and smaller, like that. It gets smaller and smaller, and smaller, like this. So this is converging down over there. This is going to be for r is greater than -1, less than 0. Yeah, and now the results, now we can just sum this all up, summarize it. So the results of example 10 are summarized below, and basically the sequence Rn is convergent if r is between, it's greater than -1, but or less than or equal to 1, and is divergent for all other values of r, and the values of the convergence. Yeah, they are limit as n approaches infinity, Rn like this, equals to, and then we can just write this as a giant bracket like this, equals to 0, converges to 0 if r is, well, greater than -1, and if it's less than 1, but remember it equals to 1. So anytime it's between absolute value is less than 1, it's going to be converging, and then this is the r equals 1 is the other one over there, and that equals to 1 if r equals to 1. So move this around here and write if. Alright, so that was a pretty extensive example. So now let's jump to a new definition or concept, and that's called monotonic sequences, and just again more terminology. So definition 4, a sequence A of n or an is called increasing if a of an is greater than an plus 1. Actually, we'll have the other way around. Less than. Yeah, so it's increasing if an is less than the next term above it. So an plus 1 for all n greater than equal to 1. Yeah, for example, i.e. if what we'll have is a1 is, well, less than a2, and this is less than a3, and so on, and this is less than a4, less than ... In other words, this right here is increasing. So these are getting bigger and bigger, like that. And vice versa, it is called decreasing if the opposite is the case, if we have an is greater than. So if the an is greater than an plus 1 for all n. For all n is greater than or equal to 1. In this case here, what we have is, well, i.e. a1 is greater than a2, greater than a3, greater than a4, greater than ... etc. And this is going to be, well, decreasing. Each one's getting smaller and smaller, decreasing. And then lastly, this definition, basically, it is called monotonic if it is either increasing or decreasing. So monotonic stems from mono or one or singular. So in other words, it's moving just one way, either up or down. And now let's look at an example to illustrate this. So example 11, evaluate whether the following sequence is either is increasing or decreasing, and hence monotonic. So we have this sequence 3 over n plus 5. So what we notice is, well, this one's obviously going to be, well, decreasing, because then if you put larger and larger n, you're just going to be dividing by a larger and larger number. So we have decreasing. decreasing because what we can have here, if we put a bigger number here over the next step, what we'll have is 3 over n plus 1. So we go to the next term, plus 5. This is equal to, well, 3, and then n, and 1 plus 5 is 6. So 6. In other words, this is, well, obviously going to be less than 3 over n plus 5, because this denominator is just, well, larger. Larger denominator. Yeah, so that's what we end up having is, thus, yeah, an is, well, this is going to be greater than the an plus 1. An plus 1. So thus it is, well, decreasing this way to the right. And this is, again, for all n is greater than 1. So yeah, it doesn't matter what you put in. Put n is 100, you're just going to get divided by 100 plus 5, which is 105. Yeah, so much, much smaller. Alright, so yeah, that was a very interesting example. So now let's look at another example, example 12. And this one states, show that the following sequence is decreasing. And we have an equals to n divided by n squared plus 1. Alright, so there's actually two ways of solving this one. Here's one of the ways. Solution 1, we must show that an plus 1 is less than an. In other words, it's going to be decreasing. That is, well, let's just put in an an plus 1 inside here. So we get a n plus 1, divide this by an n plus 1 squared plus 1, like that. And we have to show that this is going to be less than, well, n divided by n squared plus 1, which equals to just an. So we have to show that. And now what we could do here is, well, we can cross multiply. So, write this better. Cross multiply. To get rid of the denominator, multiply by, right here, n squared plus 1 times it by this one over there. So n plus 1. Like this, and n plus 1 all squared plus 1, like that. So we're going to multiply by this on both sides so that we can cancel out the denominators. So what we end up getting is, this one here is going to be, well, n plus 1, and then times it by this one, n squared plus 1. Because, well, this one would cancel out. So this one would cancel out with this, and then this would cancel out with this on the other side. So we have less than, and then we have n times it by this whole thing over there. N plus 1 squared plus 1, like that. And now we'll just expand this out. So basically we need to show that this is the case. So what will happen is, if we evaluate this, multiply n times n is going to be, what we have is n, well, n times n squared is n cubed plus, and then this one times this, so n times 1 is n. Then this one here, 1 times n squared is just plus n squared, and then 1 times 1 is just 1. And then this can be less than, now multiply this out inside, so we have n times by, and also let's just expand this one out. This is going to be n squared plus, well, 2n, so n times 1 and 1 times n, and then plus 1 times 1, like that. And then also multiply this n over there, so that's be plus n, like that. So this is what we have so far. We can easily cancel this one out like that. So then what we end up having is n cubed plus, this is n squared, plus 1, this can be less than, multiply this out inside, n cubed plus 2n squared plus n. So now what we have is, well, this cancels with this, and then this, well, we can just subtract it over this one, this cancels with that, so what we're left with is 1 is less than n squared plus n. So that's what we have here, but notice now, since we know that, well, n is just a positive integer, n is greater than or equal to 1, then this, again, we're assuming it's always positive integer, unless stated otherwise, so it's greater than or equal to 1. Then what we end up having is this part right here, n squared plus n is, well, greater than 1, because it's going to be, the lowest one could be is 1 squared plus 1, that's going to be 2. So it's greater than 1, thus, this statement right here, this is true. So this is true. We'll put that there, put an arrow. So thus this statement is true. Whoops. Yeah, I'll write that again. So is true. and put a caps lock actually, like that. So this statement is true, and thus what we have is, so this statement is true, thus this is in fact less than it. So yeah, so on our what we wanted to show is true. So a n plus 1 is less than n, so there's no contradictions inside here, and thus it's true. So thus a n plus 1 is less than a n, and then because it's less than, we have a n, the sequence is decreasing, like that, and just put an exclamation mark. Fascinating stuff like that indeed. Yeah, and now we could solve this exact same problem, but in another way. In this one, we could use derivatives. So we could prove that this is decreasing. Instead of doing it this way, use derivatives. So consider the following function, and this will be part of solution 2. So let's say we have f of x. It's going to be just writing the sequence in function form. So instead of this for positive integers, we'll write it for all real numbers. So f of x equals 2x over x squared plus 1, so replace n with x, like that. And now what I'll do is, well, recall the quotient rule, or yeah, for derivatives, so quotient rule, and this is the derivative. Recall that if we have a function like this, f of x equals 2 g of x over h of x, where these are differential functions, where the bottom can't equal to 0, otherwise, again, we'll have undefined. What we'll have is the derivative of this is going to be equal to the derivative of the numerator, the g of x, g prime of x, like that, times it by h of x, the denominator, subtracted by now the derivative of the denominator, h prime of x, times it by, well, g of x, like that, and then all divide this by, yeah, so all divide this by h of x, all squared, like that. Yeah, so basically we're going to find the derivative and see if it's increasing, or see if it's positive or negative, to determine if the function is increasing or decreasing, again, by the recall. I believe that's the first derivative test. Anyways, so let's just take this derivative, just for convenience, use the quotient rule. So f prime of x is equal to the derivative of x, the numerator, is g prime of x, so that's just going to be 1, times it by the denominator, x squared plus 1, and now minus the derivative of the denominator, which is x squared plus 1. Derivative is going to be h prime of x. That is just going to be, well, x squared is 2x, and 1 is 0. And then times it by just x, like that. Just times by x, I'll just put a squared there. Then divide this by this squared. X squared plus 1 squared. I'll put a regular bracket. Squared. Yeah, so now what we have here is, well, simplify this. This is just remove the 1, remove the brackets. It's 1 times what that. Doesn't change anything. So now we have x squared, and then this is a minus 2x squared. So this cancels with this. So what we're left with is, well, just 1 minus x squared. All divide this by x squared plus 1 squared. And now what we notice here is, well, this denominator is positive. This one here, if it's greater than 1, if it's equal to 1, we have 1 minus 1 is 0. But if it's greater than 1, this is going to be less than 0, this whole thing. For x is greater than 1. For example, if you have 2, you'll have 1 minus 2 squared, and 2 squared is 4, so 1 minus 4 is negative 3. Thus, this is going to be negative. So in other words, if the derivative is negative by the first derivative rule, I believe that's what it is. So thus we have the function is decreasing because the derivative is negative. So thus this is decreasing, and decreasing on the interval 1 to infinity, and that's open interval, because at 1 it's just equal to 0 or just flat line. So, but still it can be decreasing after that. And so f of n, this is just the same thing as an, but applying a positive integer here. This is going to be, well, greater than f of n plus 1, like that. So in other words, we are decreasing this way. So moving to the right is decreasing. Thus we have an, which is just, again, the function function f of n, where n is just positive integer, and f is just this f of x, like that. But instead of x, we use positive integer n. So we have an is decreasing, like that. And yeah, let's just box this in. Alright, and now let's move to more definitions and go over bounded sequences. So yeah, let's go over bounded sequences and go over definition 5, which states a sequence AN is bounded above if there is a number such that the sequence, all the terms AN are less than or equal to M, and this is for all positive integers. So n is greater than 1, greater than or equal to 1. Yeah, so that is a definition of bounded above, and it's called bounded below if there is a number m such that m is less than or equal to every single term of the sequence an for all positive integers, or all n is greater than 1, greater than or equal to 1. And yeah, just denote them by lowercase m for the bounded below and uppercase m or capital M for the bounded above. And then finally in the definition it says, if it is bounded above and below, then the sequence AN is a bounded sequence. So yes, very, very interesting. So yes, if it's bounded both, then it's strictly just called bounded. And that's the definition, put a line over there. So for instance, the sequence AN equals to n is bounded below because AN is well greater than 0 when n is equal to 1. That's the lowest one it could be, 1, then it goes 2, 3, 4, etc. But it's not bounded above because you can always get a bigger and bigger number because n goes to infinity. And the sequence AN equals to n divided by n plus 1 is bounded below and above, so it's bounded so it's a bounded sequence since an is greater than 0 and less than 1. Yeah, so if you recall, I covered this particular sequence several times in this video earlier, and yeah, it's a sequence that this one, as you get bigger and bigger, as n goes to infinity, you're going to have infinity over infinity. They approach 1 and it goes to infinity, and also the lowest number. Yeah, the lowest number here, you could see that if you put 1 in there, 1 divided by 1 plus 1 is 1 over 2. So the lowest could be is actually 1 over 2. Yeah, so it is. Yeah, so it is bounded because it's greater than 0 and less than 1, or greater than or equal to 1/2. But anyways, for all n. Yeah, so now going further, we know that not every bounded sequence is convergent. So just because it's bounded does not mean it has to be convergent, or meaning there's a limit. And an instance is shown below, which I covered earlier. So remember, an equals to -1 to the power of n. This satisfies being bounded because it is an, it's less than or equal to 1. Remember, it just alternates between -1 and 1, and it's greater than or equal to -1, but it is divergent. It is divergent, and this is as in example 6. Yeah, from example 6, which I covered again, which it alternates from -1 to 1, so never actually approaches a limit. And now going further, we also know that not every monotonic, again, remember that's increasing or decreasing, so not every monotonic sequence is convergent. And yeah, for example, an equals n, well, this approaches infinity, even though it is increasing. It's always getting bigger and bigger, 1, 2, 3, 4, but it's not convergent, so there's no limit. It goes to infinity. But if a sequence is both bounded and monotonic, then it must be convergent. And this fact is proved as the following theorem, as I'll go into it. But intuitively, you can understand why it is true by looking at the figure below, and it's yeah, pretty straightforward why it should be, because it's always increasing or decreasing, and there's a limit. I mean, and it's bounded, so bounded below and above. So it has to be, yeah, approaching a limit that's going to be less than whatever it's bounded by. So for example, yeah, let's just graph this out. Let's say there's an on this chart, and let's say it is bounded below. So it's bounded below, yeah, actually, I mean bounded above. So bounded above, so an is always, every single term is going to be less than or equal to m, so capital M there. So let's say it's bounded like that. So it can't go above this one, but the sequence is always going to be increasing. Yeah, so it's monotonic, so let's assume it's increasing. So it's going up like this, it's going up. But eventually, because there's a limit, it can't get anywhere near there, so there has to be a limit like this. Where L could equal M if it has to, but it just can't be bigger than that. So then it has to converge somewhere. So it's bounded by L and M, and L could be M. It depends. And again, this is just increasing, and it has a limit. because it's bounded, so i.e. monotonic. Monotonic. So if it's increasing or decreasing, it's monotonic or one way moving. Yeah, so yes, this was a very good intuitive illustration. So basically, if an is increasing and an is less than or equal to m for all n, so it's bounded above, then the terms are forced to crowd together and approach some number L, which could even equal to m. So it's always increasing, but it's still approaching a limit. And the proof of the following theorem is based on the completeness axiom. Yeah, just to prove it in more mathematical rigor. So it's the completeness axiom for the set R of all of real numbers, which says that if S is a non-empty set of real numbers that has an upper bound, yeah, so that X is going to be less than or equal to M for all X in S, then S has a least upper bound B, which means that B is an upper bound for S. But if M is any other upper bound, then B is less than or equal to M. So yes, that's a lot of mathematical mumbo jumbo. I'll illustrate this in a bit more detail soon, just to make some sense out of this. So the completeness axiom is an expression of the fact that there is no gap or hole in the real number line. Yeah, so for example, let's say we have a number line like this. There's X, there's 0, example, and then let's say we have a set R of real numbers, or all real numbers. Let's just say that S is everything. It goes on and on. This is, R is everything. So this is a set of all real numbers. Like that, it goes everywhere. And then which says S is a non-empty set of real numbers that has an upper bound M. Yeah, so let's say S, yeah, so it has an upper bound M. So what we'll do is, will be a set of real numbers from all the way to the left. And then moving all the way to, but instead of all real numbers, like this, we get all the way up to here, which is M. And this is S. And I'll draw S like this. It indicates it's a set, so it stops right across over there. Yeah, so that is bounded above, but it's pretty much similar to this one, where that's L is going to be considered, could be considered as a least upper bound. That's the upper bound there. So what we have is, then there is a, or then it has a least upper bound B. So let's say it has a value B like this. Yeah, so any number you pick B like this, it's going to be less than M. Yeah, if this is the least upper bound, so if it's, if we say it's less than this one, but if M is anything other than B, then it's obviously going to be, well, between this. This is basically all it's saying, that B is always going to be less than or equal to M. Yeah, so essentially this is the same thing as this one. So this B could be viewed as L, like that. So that is the upper bound or the limit. But if an upper bound exists, that's then it's, if another upper bound exists that is not the limit, then it's obviously going to be less than the upper bound there. So that's pretty much what it's saying. Yeah, so essentially this stems from what's called no gap or hole, and that means that every number can have infinitely amount of numbers past the decimal place, hence a least upper bound B can always be found that is B less than or equal to M. So yes, just go over just a quick mainstream view of this completeness axiom. Is very interesting. Again, this is more rigorous mathematics. So completeness of the real number. Intuitively, completeness implies that there are not any gaps in Dedekind's terminology or missing points in the real number line. This contrasts with the rational numbers whose corresponding number line has a gap at each irrational value. In the decimal number system, completeness is equivalent to the statement that any infinite string of decimal digits is actually a decimal representation for some real number. Yeah, so depending on the construction of the real numbers used, completeness may take the form of an axiom, the completeness axiom, which is stated above there, or maybe a theorem proven from the construction. There are many equivalent forms of completeness, the most prominent being Dedekind's completeness and Cauchy completeness. And completeness is a metric space. Very, very interesting stuff. Yeah, I might go over that later, but I'll just stick with the axiom for now. Yeah, so essentially it's saying, mathematically, make an axiom saying that a limit exists if there's an upper bound and the function is always increasing. Or in decimal places, if you keep adding numbers to the decimal, the number is increasing. But it's still approaching a limit. And that limit could be M, but it's going to be less than or equal to whatever it is bounded by. So anyways, let's go further. So now that all this was for the monotonic sequence theorem, which is stated above, but now write it as a theorem. Every bounded monotonic sequence is convergent. So every bounded, so has an upper and lower bound. upper or lower bound, and it's monotonic or increasing, or increasing or decreasing, then the sequence converges to a limit, or is convergent. And here is the proof. So suppose AN is an increasing, hence monotonic and bounded sequence. Yeah, so if it's increasing, hence monotonic and bounded, that means, well, since AN, since AN is bounded, so it's bounded and it's increasing, hence it has an upper bound. The set, so put the set S, make it all the numbers inside AN, where n is greater than or equal to 1, then this has an upper bound. Yeah, so this has an upper bound. An upper bound because because it is bounded. So it's bounded and it's always increasing. Yeah, so by the completeness axiom, it has a least upper bound. We'll call that L. Again, BL is, as I said, is essentially the same thing in both the illustrations above. So given that epsilon, so if you're given a number, epsilon greater than 0, then L minus E is not an upper bound for S. Yeah, since L is the least upper bound, and L minus E, L minus epsilon is less than the least upper bound. It's because we're subtracting 1 from it. So therefore, if we have this number number epsilon, so that's what we have is A, and we'll have a capital N, is greater than L minus epsilon for some integer N. Capital N, like that, because there's a least upper bound exists. And this is this number is less than. So if we're given there's a number less than it where the term is less than L, then we have to have some integer capital N where a n is greater than this this value right there, L minus this epsilon. But the sequence is increasing because it's monotonic, and we're assuming it's increasing right here. So AN is greater than or equal to a capital N for every n is greater than n. So then, so if we have n if n is greater than capital N, then it's always going to be bigger than this value there. So thus, if n is greater than, if n is greater than capital N, we have, AN is greater than or equal to, a capital N, where this one already we know is going to be, greater than the least upper bound minus this epsilon. So that's what we have, is just take these two terms. This one is going to be now AN is greater than L minus epsilon. And now what I'll do is just rearrange this, write epsilon on its own. So move this over to this side, move this over to this side. So then what we end up getting is we get epsilon is greater than L minus AN. And now this value right here, this has to be greater than or equal to 0. And this as well, since we know that this is the least upper bound. So that it says, so since AN is going to be less than or equal to L, so it can't be anywhere any larger than it. So it's always going to be a positive number. Put that bracket like that. And now I'll just flip this around, rearrange this, or writing it as 0 is less than or equal to L minus AN, and less than epsilon. Just write it this format, so it's greater, make the 0 on the left side. Yeah, so thus what we have is, thus the absolute value, this is going to be greater than 0, or we could write this as the absolute value of L minus AN is going to be less than epsilon, and this is whenever n is greater than capital N. Again, as above here. So in other words, we have the limit. This is the definition of the limit. And we have limit now as n approaches infinity, as AN equals to L. So that's just a definition of the limit. So yes, very interesting, just using the mathematical rigor of the axiom theorem to apply it and show that it's essentially the same thing as the limit there. So it proves that there's a limit for a monotonic and bounded sequence. So yeah, every bounded monotonic sequence is convergent, so it converges to a limit. So a similar proof using the greatest lower bound instead of the upper bound for the other side works if an is decreasing. And the proof of the above theorem shows that a sequence that is increasing and bounded above is convergent. Likewise, a decreasing sequence that is bounded below is convergent, whereas a greatest lower bound as opposed to the least upper bound. And yeah, so that's going to be one to the left of the number line. And yeah, this fact is used many times in dealing with infinite series. Alright, so now let's go over another example that's very, very interesting and pretty extensive. And it's going to be the last example before I go into the exercises at the end of the chapter section of my calculus book. Yeah, so this is the last example they have, and before I get further down to this video. So, example 13, investigate the sequence an defined by the recurrence relation a1 equals 2, and then an plus 1 is equal to, equals to 1/2 an plus 6, for n is 1, 2, 3, etc., or just a positive integer. So solution, we begin by computing the first several terms because it's not straightforward what the pattern is. But let's just see what the pattern is. So a1, the first term is equal to 2, then a2, we have 1/2, and then an, which was 2 plus 6, that's 8, divided by 2 is 4. Like that, so that's 4. And now let's look at a3. a3 is equal to 1/2 an, which is a2, which is 4. 4 plus 6, this equals to, 4 plus 6 is 10. Is 10 divided by 2 is 5. Like that. So the next one, let's write a4. a4 is equal to, again, 1/2, and then a3, which is 5, plus 6. This is going to be, it's going to be 11 divided by 2. That's just, well, 5.5. And then a5 now. Yeah, so now a5 equals 2 is 1/2, and then take the a4, which is an, and this is going to be 5.5 plus 6. So in other words, this is going to equal to, well, what is this? 6 plus 5 is 11, so 11.5 divided by 2, and I'll just calculate this out, save time. So let's delete this. Yeah, so there it is. I've just calculated out here, and you can see using the amazing built-in calculator in my OneNote, you can just erase this and press equal, and automatically solves it. So that's just the 11.5 divided by 2 is 5.75. Then put that 575 inside here. Then plus 6 divided by 2, we get 5.875. And throw that in there. For a7, we get 5.9375. Throw that in there, we get 5.96875. Throw that in there, and then we get for a9, 5.984375. As notice, it's approaching, it looks like it's approaching 6. So I'll write that down. Approaching 6. So very interesting. So these initial terms suggest that the sequence is increasing and the terms are approaching 6. To confirm that the sequence is increasing, we can use mathematical induction. So note first that mathematical induction is often used in dealing with recursive sequences. And yeah, I'll illustrate that first. So first, recall from earlier videos the principle of mathematical induction, just to get a quick recap. So mathematical induction: in proving statements that involve a positive integer n, it is frequently helpful to use the following principle. Principle of mathematical induction. Let Sn be a statement about the positive integer n. Suppose that S1 is true. And so if S1 is true and Sk plus 1 is true whenever Sk is true, then Sn is true for all positive integers n. So in other words, if the first one is true, and then this random one, k plus 1 is true whenever Sk is true, then it all has to be true. And this is reasonable because since S1 is true, it follows from condition 2 with k equals 1 that S2 is true. Then using condition 2, k equals 2, we see S3 is true. Again, using condition 2, this time with k equals 3, we have that S4 is true. And this procedure can be followed indefinitely. So let's illustrate that over here. So let's apply mathematical induction to show that an plus 1 is greater than an for n is a positive integer greater than or equal to 1. So in other words, we're going to show that it's increasing. Yeah, we're going to show that as n gets larger, this gets bigger and bigger than the previous number. So to do that, let's look at the first statement. So S1, but in this case, we have A1. So A1 is equal to 2. So A1 is equal to 2. And then we know that A2, this equals to, well, 4. Let's just scroll up. So A2 is, A2 is equal to 4. So we have 2 and 4, so that's true. Yeah, so thus, A2 is greater than A1. And yeah, so thus, the statement AN plus 1 is greater than AN is true. So is true for n equals to 1. So we have the initial case, it's true. Yeah, so now if we assume, so now we know the initial case is true, so if we assume that an plus 1 is greater than an, or in other words, is increasing, this is true, so we assume it's true for n equals to k, or for all n equals k, then we have replace n with k, so we have a k plus 1 is greater than a k. So if this is true, what we can do is, so we can add, now just add a 6 to this. Add a 6 to both sides, so plus 6 to get to the other term. AK plus 6, and then divide by 2 to get to the other term. So now we have 1/2 AK plus 1 plus 6 greater than 1/2 AK plus 6. And the reason we did that is, well, this is now just AK plus 2. And this I did it to both sides, so we never changed the sign, doesn't need to change there. So this is going to be now over here is just AK plus 1. So that's just AK plus 1 there. So in other words, what we just proved is, well, thus, AK, I'll put the thus further out. So thus, just line up with that, AK plus 2 is greater than AK plus 1. So if we assume this is true, what we end up getting is this is also true. But we know that this is true. So then the second one is true, the third one's true, the fourth is true, the fifth is true, and so on. So that's what we just proved it. Yeah, so thus we have deduced that an plus 1 is greater than an is true for n equals to k plus 1. So when you add k equals plus 1 there, and this all we did was assume for n equals to k. So 1 larger is also true. So therefore the inequality is true for all n by induction. Next we verify that an is bounded by showing that an is less than 6 for all n. Yes, the mathematical induction we show that it's always increasing. Yeah, now we just have to show that it's bounded. So then to prove that it's less than 6 for all n. Since the sequence is increasing, we already know that it has a lower bound, and the lower bound is the first term. That's just an is greater than or equal to a1 equals to 2 for all n. And we know that a1 is less than 6, because n 2 is obviously less than 6. So the assertion is true for n equals to 1. So the initial case is true. So suppose it is true for n equals to k. Yeah, so suppose, now we're going to use mathematical induction again, suppose AK is less than 6. So if AK is less than 6, so we have I do the exact same thing, AK plus 6, then put a 6 plus 6 equals to 12. So do the same thing on both sides, and I'll put n, just make it all in uniform as from above. So we have 1/2 AK plus 6, that sign stays the same. This is going to be 12 over 2 is going to be 6. So in other words, this right here is just AK plus 1 by the recursion relation. So thus, what we've proven is AK plus 1 is less than 6. So in other words, we assume this one is true, then this is true. But we know that, again, we know that it's true for the first one. So A1 is less than 6 because A1 is 2. So then A2 is less than 6. A3 is going to be less than 6 because of this one. Every time you add 1 to it, it's always going to be less than 6. So thus we've proven that it's always going to be less than 6. Yeah, so this shows by mathematical induction that an is less than 6 for all n. Since the sequence an is increasing, i.e. monotonic and bounded, the monotonic sequence theorem guarantees that it has a limit. The theorem doesn't tell us what the limit is, but we know it has a limit and it's bounded by 6. But now that we know that the limit exists, we can use the recursion, the recurrence relation to write. We could write limit as n approaches infinity of an equals to L. So we write this as a limit like that. So thus what we could also do is, thus we could write now the limit as n approaches infinity of 1 larger than that, so an plus 1, and just use the recursion relation. This just equals to limit as n approaches infinity of, and now we could just have the 1/2 and then an plus 6. Yeah, alright, so now that we have this limit, well, we could keep going further and then use limit laws, put this limit inside. So this equals to 1/2 of limit as n approaches infinity, and then this is of an, like that. And then we can just have a plus 6 over here. Okay, so now that we have this one, well, we know this is just L. That's just L. Like that, or I just put an arrow like this. Draw a better arrow. Like that. Or just fix that up, fix the arrow up like that. So now this equals to, well, 1/2, or I'll just make it like this, L plus 6 over 2, or 1/2 times L plus 6. And now, well, since an is approaching L, it follows that, well, it follows that, yeah, that follows that an plus 1 is also approaching L too. Because, well, this is the limit is L, so then any number or any term bigger than an, like an plus 1, that's also approaching L. The terms are approaching L. Yeah, basically, i.e., as n approaches infinity, so too, yeah, basically n plus 1 also approaches infinity, or infinity plus 1, same thing, 2. And for a rigorous proof of this one, just a more rigorous proof than this, it's pretty obvious it should be L as well. So a proof of this fact is shown in exercise 1 at the end of this video, so stay tuned for that very shortly. Yeah, so thus what we have is, well, this limit is also equal to L, so thus what we have is L, the limit over there, equals to L plus 6 over 2. And then what we could do is, well, move the 2 over to this side. We get now 2L equals to L plus 6. Cancel the L, cancel this. In other words, what we get is L equals to 6. Absolutely amazing. Like that. And this is hashtag absolutely. This deserves a full writing. Amazing. So all that mathematical rigor, the mathematical induction, all this mathematical mumbo jumbo, and we finally got to the answer L equals 6, which seemed obvious from just the terms writing it out, but mathematically writing it out is pretty epic indeed. It's fascinating stuff. And this is actually why I started doing a lot of mathematics early on in my years, basically applying all this mathematical rigor and the mumbo jumbo, or whatever you want to call it, to get what we pretty much knew already there, but still, nonetheless, you can apply mathematical proofs to whatever problem you want to identify and solve, and then go through as much work as possible to finally prove without a shadow of a doubt that is the limit is a 6. Alright, so now that we finally finished the end of this section in my calculus book that went over the concepts and the examples, and now I will solve some of the proofs and exercises that were alluded to earlier in this video. And the following exercise, exercise 1, proves the statement used in example 13, which was the one we just went over right now, which would have the limit, if the limit n as n approaches infinity of an equals to L, then so does the limit as n approaches infinity of an plus 1. And basically, because as n approaches infinity, so does n plus 1 approach infinity. So we're just dealing with the exact same limit over there. So since an approaches infinity, it follows that this also. So yes, very, very interesting. And I'll prove that more rigorously, even though it should be fairly straightforward. So part A of this exercise 1, if an, the sequence, is convergent, show that the limit as n approaches infinity of an plus 1 equals to the limit as n approaches infinity of an. And then part B goes over an example and says a sequence an is defined by a1 equals 1 and an plus 1 equals to 1 divided by 1 plus an for all positive integers, or n is greater than or equal to 1. And assuming that an is convergent, find its limit. So let's look at A right here. So an is part A, the sequence an is convergent. Show that we have this scenario. First of all, let's jump to the definition. So first of all, recall from definition 2 from earlier in this video, the precise definition of a sequence, which I have just copied and pasted from my calculus book for convenience. So we have it right here. So definition 2, a sequence an has a limit L, and we write limit as n approaches infinity of an, this equals to L, or we could write an approaches L as n approaches infinity. If for, and there's operative word, so if we have the scenario, if for every number epsilon, which is epsilon is greater than 0, there is a corresponding integer capital N, such that if there's any integer greater than this capital N greater than capital N, then the difference an minus L, the absolute value, or the difference from the sequence and the limit, is less than this number, epsilon. So in other words, we can make this extremely small because this is for every number epsilon greater than 0. So if we make this extremely small, very close to 0, then if there's always a integer capital N, such that if you increase integer greater than it, then the difference between the sequence and the limit just gets smaller, or less than that number, which is already greater than 0, but very, very small. So thus the difference is approaching 0, then by definition, this is the limit. The limit exists and equals L. But now what we could do is, well, now if we replace n with n plus 1 in the above definition, what we end up getting is, well, we'll look at this part right here. So we'll look at if, so we just replace it. So if n plus 1 is greater than n, then what we end up having is an plus 1 minus L is less than epsilon. And now this is pretty much exactly the same thing, but now we can just rewrite this one, or n is greater than, move that 1 on the other side, n minus 1. Yeah, so in other words, what we have is this right there, and this is exactly the same thing, but instead of a corresponding integer capital N, we have the corresponding integer capital N minus 1, or just make it a bit easier to see for visual purposes. So let's say we have capital M equals to n minus 1. Yeah, so thus what we have is, if n plus 1, not n plus 1, if we have n is greater than capital M, then what we have is a plus 1, if we have the scenario, minus L less than epsilon. So we haven't changed anything. This is now we're dealing with M. Instead of n is exactly the same thing. You just write the z if you want. It doesn't matter. So thus, by definition, so if we have the scenario, by definition, what we end up having is the limit as n approaches infinity of an plus 1 is equal to L. Yeah, so that's what we have there. And also, since, well, L is just equal to, by definition there, limit as n approaches infinity of an equals L. So thus, we've just proved it. Again, thus, we have limit as n approaches infinity of an plus 1 is equal to limit as n approaches infinity of an. So they're one and the same, and they both equal to L. So limits equal each other. And I'll just put an equals L here for completeness, equals limit, like that. Alright, so now let's look at, well, I'll write question part B. So now part B. So if we scroll up to part B, what we have is right here. Part B says if a sequence an is defined by a1 equals 1, and an plus 1 equals to 1 over 1 plus an for all positive integers n greater than or equal to 1. Assuming that an is convergent, find its limit. So let's write this down right here. So a1, what we have is, so we have an is convergent. It's convergent, so it has a limit. And we have a1 is equals to 1. And then an plus 1 is equal to 1 over 1 plus an for n is greater than equal to 1. So the positive integers. Let's see if I wrote that correctly. Yeah, so we have that written correctly. Yeah, so thus since it is convergent, what we have is limit as n approaches infinity of an equals 2, again by part A. So this is going to be limit as n approaches infinity of an plus 1. And these both equal to L because it's convergent. So, yeah, so what we can write is, well, let's write the recurrence relation right there. So limit, so let's write thus. Thus we have limit as n approaches infinity of an plus 1 equals to the limit as n approaches infinity of 1 over 1 plus an, which equals to, well, we know just limit laws, this will just become, well, 1 over 1 plus L, like that. And then remember, this one just equals to L, so it equals to L. So now we have this relation. So what we can do now is multiply this over top and then solve that. So what we get is a 1 equals to L times 1 plus L equals to L squared plus L. Now we can move the 1 on to this side. So thus what we have is 0 equals to, I should write it the other way around. I'll write L squared plus L minus L is equal to 0. Just move it over to this side. And this is just a quadratic equation. So recall the quadratic equation right here. Write it quadratic. Yeah, quadratic, actually it's a T, not a D over there. So recall quadratic formula where we have, if you have a function like this, ax squared bx, plus bx plus c, where a, b, c are constants, then so we have this, then we basically have x equals to negative b plus or minus square root b squared minus 4ac, and this is divided by 2a. Yeah, so thus for our case, what we end up having is, put this down like that, thus what we have is L is equal to, so a is 1, and b is 1, so we have negative 1, plus or minus, and then we have square root, square root b squared, so 1 squared minus, so minus 4 times a is 1, and then c is times 1, and then times it by, well, c, which is negative 1, so negative 1, like that. And notice this will just add up, become positive, negative times negative, and then what we have is 2 times 1 is 1, so 2 times 1 is just 1, so this just equals to, well, negative 1 plus or minus, and then we have 1 squared is 1 plus 4 times 1 times 1 is just 4 plus 5, 4, I mean it becomes 1 plus 4 is 5, so square root 5 over 2, like that. Yeah, and so what we have is, well, since L is greater than 0, actually, you can just scroll up above here, where is, I mean it's greater than or equal to 0, so it's over here, right here. So an plus 1 over 1 plus an. So it's always going to be positive. So it's never going to be never going to be negative, because these integers are always going to be positive. So it's greater than or equal to 0. So since this, then actually to more completeness, or more complete, I'll write L is greater than or equal to 0 if it exists for this function. Otherwise, the function is wrong. Then we'll just take the positive, because if you minus the square root 5, that's going to be greater than 1, and well, whatever it is. If we're subtracting negative 1 minus any number, it can be negative. Thus, so since, if it exists, then what we have is L equals to negative 1 plus square root 5 over 2, and there is our limit. And just now if we want to get the numerical number of this, if we plug this into just a one-note built-in calculator, so note L equals minus 1 plus square root 5 bracket, close bracket, divided by 2 equals to 0.618033, etc. Keeps going on, and also fascinating stuff. So now let's look at exercise 2, and this one states, prove theorem 2 mentioned earlier in this video, and we're given a hint, use either definition 2 or the squeeze theorem. Here is theorem 2, I just copied and pasted. Let's just scroll up to see where this was found. Where's theorem 2? How far away is it? Just want to see where it was. I'll show you there. So we passed theorem 3, and there is theorem 2. So this is the one we had written over here. And basically, if the limit as n approaches infinity of the absolute value equals 0, then we have the limit without the absolute value is also equal to 0. So let's scroll all the way back down. Fascinating stuff. I just wanted to go there to see where in the video it was. So way far up in the video. It was a pretty extensive video. So let's keep going and going. And now there's exercise 2. So there's a theorem, just to double check. So recall of theorem 2 right here. So limit like that. Yeah, so now what we could do is, well, solution 1, I'll just use squeeze theorem, and then solution 2, I'll use definition 2. So what we could do is, so if the limit of the absolute value of an as n approaches infinity is equal to 0, then what we can even write is, so if limit as n approaches infinity, an absolute value is equal to 0, then what we could write is the limit as n approaches infinity of negative a absolute value of an. This equals to, we'll just use limit laws, take the negative out. This becomes, well, negative. Now limit n approaches infinity of an just equals to, well, this is 0. So negative 0 just equals to 0. So yeah, that just equals to 0. And since we have negative an, negative absolute value of an is going to be, well, less than or equal to an, where this is less than or equal to the absolute value, because remember, that's always, just make it always positive. This one's always negative, so that's always going to be less than or equal to an. So now it gets squeezed inside. So thus we have, thus limit as n approaches infinity of an, well, this is, remember, both of these are going to 0. This is going to 0. This is going to 0. This one gets squeezed, has to go to 0. So thus limit as n approaches infinity of an equals to 0 by the squeeze theorem. So yes, the squeeze theorem is quite amazing. It's very straightforward and quick. So there it is. Yeah, so now let's solve this very same theorem, but now use solution 2. I mean, look at solution 2, which is using definition 2, which is, again, a precise definition for sequences, as illustrated in exercise 1 as well. So we have here definition of sequence. An has this limit, and we write the limit as n approaches infinity of an equals L, or an approaches L as n approaches infinity. If for every epsilon, number epsilon greater than 0, there's a corresponding integer n, capital N, such as we have this case. If an integer, if any integer n greater than, or I mean, if all integers n greater than capital N, then we have this scenario: the difference an minus L, the absolute value is less than this epsilon. Then this is the limit. So again, just recap it. I also need to recap it because sometimes this takes a while for the precise definition. The terminology that mathematics book or the calculus book uses is. Yeah, it appears non-intuitive, but once you dig your head into it, it's pretty straightforward. So if we use this definition, but in our case, so L equals to 0 in our case, because we have, the theorem is the absolute value is equal to an equals 0. So we're looking at that. So the limit is 0, and also we're dealing with absolute value. So what we have is, so in our case, we have this and, let's write and, so we have limit as n approaches infinity of absolute value of an, like this, equals to, well, 0, and this is if n is greater than capital N, then n minus 0, like that, epsilon. Or in fact, to be more complete, we'll write this as an absolute value here. So we'll have absolute value of an minus L, like this, less than epsilon, but this becomes, well, this becomes absolute value of an minus 0. So the 0 just goes away, which equals to, this one becomes, well, absolute value of an, just to illustrate the point, which is the same thing as writing absolute value of an less than epsilon. So in other words, this is the same thing as removing the absolute value sign. Same thing. Yeah, so thus this fits also for fits. So this definition fits also for removing the absolute value sign. So limit as n approaches infinity of, well, an, and this just equals to 0. So yeah, if we have this, is exactly the same thing. we're gonna have we're gonna have the exact same scenario where n is greater than n, then we have this scenario of but instead of that we just remove that an, so we have this exact same thing. Yeah, so thus we have limit as n approaches infinity of absolute value of n of an if this equals 0. This also equals to the limit as n approaches infinity of an, like that. So yes, there's the theorem. And here's for completeness, let's write the definition inside this little bubble here as well. If n greater than n, then we have an minus L less than epsilon becomes, well, an minus 0 equals to an, like that. Same thing, less than epsilon. So yes, fascinating stuff indeed. So thus the limits are one and the same. Yeah, and now let's look at exercise 3, and this one looks at proving theorem 3, also mentioned earlier. And let me just quickly scroll over there to see where it was first brought up. Theorem 3, just keep going somewhere in the middle. Let's see where this one is. Example 211, monotonic sequence. And there is theorem 3. So if limit as n approaches infinity of an equals to L, and the function f is continuous at L, then what we have is, well, limit as n approaches infinity of f of an equals to f of L, and keyword number is continuous. I'm going to prove this theorem in exercise 3, and I'll get to that in a bit. And recall that I used it for this this example where we have sine of a sequence, and we could just, well, we know the limit of the sequence, we could just throw that inside. So we do the sine of the limit inside and solve it very quickly, like that. So let's just scroll back down and solve this, or prove that it is the case. All right, almost there, and yeah, we're right here. So prove theorem 3, also mentioned earlier. So recall theorem 3, as I just went over, limit as n approaches infinity of an equals L, and the function f is continuous at L. Then we have this scenario that the limit as n approaches infinity of f of an equals to f of L. And here I just copied and pasted from my calculus book just for convenience. So what we know here is, well, since we're given the limit, so since limit as n approaches infinity of an equals to L, yeah, since we're given this, then we must have, by the definition of sequences, then we must have, so we must have a number, I'll write this, a number epsilon greater than 0, or actually written better, if for every epsilon, or a number epsilon greater than 0, there is an integer, or a corresponding integer, as I went over this definition many times, capital N, such that if, another if integer n is greater than this capital N integer, then we have the difference, an minus the limit L is less than the number epsilon. Yeah, so since this is the case, since we were given the limit of an as n approaches infinity is L, then we must have, for any number epsilon greater than 0, there's integer n, such that when you get larger than this integer, the difference an minus L, the absolute value of this difference, is less than the number epsilon. So whatever it is, you can make it extremely small, again, as I've stated many times. So if you make it extremely small, then there's always going to be a integer n, such that if you get larger than that, then the difference gets smaller than that number that you picked, even if it's really small, again, because the limit by definition exists. And also, since we are given that, since f is continuous at L, yeah, so this at x equals L, or at L, so it's continuous at L, then what we must have, and I'll write here then, by definition, by, again, another precise definition of limits, or here I wrote it a bit better, I just typed it out. So, and since f is continuous at L, by the precise definition of limits shown in my earlier videos, we must have the case right here, the limit as as x approaches L of f of x must equal to, well, f of L. So the limit exists in the function f of L equals to, the limit as x approaches L of f of x equals to f of L. If here, if for, again, similar to the above definition for sequences, if for every number epsilon greater than 0, there is now, instead of an integer, there is a number. We'll call this delta. So again, number versus integer. Number delta such that, actually I'll separate this as a number delta greater than 0. It's also greater than 0, such that, if we have, if the absolute value of the difference x minus L is going to be, if it's less than this specific number delta, whatever it is, greater than 0, then again, instead of going just n larger than capital N, because we're going to a specific point as opposed to going to infinity for these limits, we're going to go, we're moving to L, so we're just looking at the interval but at L, so very, very small. Then the scenario we have is then f of x minus f of L. This difference is going to be less than this epsilon number. So that was a definition, but what I'm going to do is I'm going to just correlate these better with this above. So what I'm going to do is I'm going to replace, just switch these around. Switch the terminology. I'm going to call this delta, call this epsilon, so that this is going to be delta, and this is epsilon, so that these line up. Notice how this is going to be exactly the same thing if we let an equal to x. So thus what we have is, well, that's the definition of continuous. So thus, let's just say, suppose now, so suppose we had n is greater than capital N. So let's say suppose n is greater than capital N. Then what we have is, what we have is this scenario is the case. So then we have is, absolute value of an minus L is less than epsilon. So this is what we have right here, but instead of just regurgitating this limit right here, what we could do is, we'll replace this x. If this x is just an, what we could do is, well, then this is the case, and I'll write over here actually, just write and. What I'll do is I'll write this, but as instead of x, I'll put an, and then what we have is f of an minus f of L is less than epsilon. So this way right here is, instead of x we have this one, and then it's everything of this definition lines up. So thus what we have is, so suppose this is the case, I'll just write then, or actually thus is better. Thus we're replacing x with it, so thus limit as an approaches L of f of an is equal to f of L by definition. And I'll just write that here by definition of the above continuous function. So by definition, or by precise definition. But notice this is the same thing. So a limit as an approaches L is the same thing as, limit, well, I'll just write this down. Limit an approaches L of f of an is just equals to limit as n approaches infinity of f of an. So as n approaches infinity, it'd be exactly the same thing. So again, this will just equal over there. So it equals to f of L. So yes, I'll just circle this. So hopefully you got your head around that. It's just it's pretty straightforward once you understand these precise definition terminology. But yeah, it's just pretty abstract. And precise definitions has always been a bit of a brain teaser. The way that they use these definitions, again, it's all it has to do is with when you just any number you pick, there's always going to be a number such that this difference is always going to be less than that number, and so on. So yes, so this is the same thing. So in essence, all we're doing here is, well, right here we just replace this this L with limit as n approaches infinity of an. And essentially just throw that in there, and then x would be the an, and so on. We get that. So it's pretty straightforward. Worked around the long way just to get to that same thing that we can intuitively look at. So there it is. Alright, so now let's finally get to exercise 4. This is the last of the exercises before I go over a mainstream overview of Fibonacci. And this is to do with the Fibonacci sequence. So, as I illustrated before, so part A states Fibonacci posed the following problem. Suppose that rabbits live forever and that every month each pair produces a new pair which becomes productive at age 2 months old. So every month there's a new pair, and it becomes productive after age 2 months, they live forever, and so on. And if we start with one newborn pair, how many pairs of rabbits will we have in the nth month? And then basically it states, show that the answer is Fn, where Fn is the Fibonacci sequence defined in example 3c, as I illustrated earlier in this video. And then part B states, let an equals to Fn plus 1 divided by Fn, and show that an minus 1 equals to 1 plus 1 divided by an minus 2, and so on. And assuming that an is convergent, find its limit. Alright, so now let's look at part A. So, I'll go over this rabbits ones first, but first let's recall the Fibonacci sequence defined in example 3c, and it was right here. Fibonacci sequence Fn is defined recursively by the conditions f1 equals 1, f2 equals 1, and then we have Fn equals to Fn minus 1 plus Fn minus 2, for n is a positive integer greater than or equal to 3. So in essence, each term is a sum of the two preceding terms. So f3 is going to be f1 plus f2. And the first few terms are 1, 1, 2, 2, 3, 5, 8, 13, 21. And again, you can just add these up. So 3 plus 5 is 8. 8 plus 13 is going to be 21, and so on. And 1 plus 1 is 2. So let's look at this. So let an be the number of rabbit pairs in the nth month. Okay, so we're asked here again. So suppose that rabbits live forever and that every month each pair produces a new pair which becomes productive at age 2 months. So if we start off with one newborn pair, so if we start off with, how many pairs are we left in the nth month? So let an be the number of pairs in the nth month. So clearly, we know the first few months. Clearly, a1. This just equals to, well, 1. There's one pair, and then also at the month 2, so because the rabbits live forever, but they become productive at age 2 months. So in the second month, the first one is going to be, well, it's a newborn pair, so then it's going to equal to a2. So after 2 months, there's still going to be one rabbit pair. So the first one, and then it becomes productive, and then after that, they're going to start producing. Yeah, so now in the nth month, each pair that is 2 or more months old, that is an minus 2 pairs, yeah, it's basically all of the rabbits that were around for the 2 months ago. Yeah, so 2 months ago, all the rabbits that existed then will produce new pair, and to add to the an minus 1 pairs. So we're gonna add the 2 months previous, all the rabbits that existed, all the pairs, added to all the pairs of last month's, okay, or the number of those, and we'll explain this as I illustrate it. So in other words, all the rabbits that are present from 2+ months ago multiply, so we add the total number of rabbits from that time period to the total number of rabbits from 1 month ago, since this number has no it has newborn rabbits that haven't matured yet. Those are the ones in 1 month ago, so you can't just take that number because some of them aren't going to reproduce. So thus, let's just write this down to get this pattern. So thus we have a1 equals to 1, and then a2 equals to 1, because we still have one pair, and then now a3, the total number here, and these are the third month. So the first month there's 1, second month there's 2, but then the third month what we end up having is, well, we take the ones in the first month. So the number in the first month, which was, well, a1 plus a2 now, because we're actually better than I'll write a2 plus a1, just so it's easier to write, because now what we're going to do is we're going to look at the number of rabbit pairs in the second month, which was 1, and then we're going to reproduce. They're going to reproduce. We have another 1. This is 1 plus 1, and that's because they started off at a1. So this is going to be, well, 2. And now notice how now you'll understand this pattern. So a4. So a4 is going to be, well, we initially have 2 rabbit pairs. So 2 rabbit pairs, a3. So we take all the ones from here. Now what we're going to do is we're going to multiply all the ones from 2 months previous. So this is what this one just had 1. So we just add the A2. Equals 2, 2 plus 1 equals to 3. And then A5, what we'll do here is we take all of the number of pairs from previous, so A4. And then what we're going to do is we're going to add all the ones from the previous, A3. Because these are the ones that are going to multiply. So there's 2 pairs here that are going to be matured by the time it's A5. And these 2 are going to produce 2 more. So that's going to be, yeah, so let's plus this A3. So we're going to have A3 plus 2 equals to 5. And I'll just write one more of these just to illustrate this. So now A6 is going to be, we take the previous pair, the total number of them, A5, and then plus, then we plus the ones before, there was 3. And these ones are all going to multiply. So these 3 are going to be 6. I mean, we're going to add these 3. These 3 are going to produce 3 more here. So we'll have A4, and that equals to 5 plus 3. This equals to 8, like that. And then we keep going on and on. Then what we get is AN equals to, well, AN minus 1 plus AN minus 2. Because you can see these. A3 is A2 plus A1. A4 is A3 plus A2, and so on. And this as well, this is just the Fibonacci sequence. This equals to Fibonacci sequence from Fibonacci sequence from example 3C earlier in the video. So yes. So thus the sequence AN equals to the sequence Fn from before. So this is the Fibonacci sequence. So yeah. Alright, so now let's look at part B right here. So part B, it says let AN equals to Fn plus 1 divided by Fn, and show that AN minus 1 equals to 1 plus 1 over AN minus 2. And then we're asking, assuming that AN is convergent, find its limit. Very, very interesting. Let's see what we can come up with right here. So part B. I'll write this down. Part B. Alright, so we're gonna let over here let AN equals Fn plus 1 divided by Fn. So let AN equals to Fn plus 1 over Fn. Again, where this is the Fibonacci sequence Fn. So, and then we're also asked to show, just write it down, show that AN minus 1 is equal to 1 plus 1 over AN minus 2. And let me just scroll up to see if we got the right one there. So yes, AN minus 1 equals 1 plus 1 over AN minus 2. So let's go ahead further. Yes, first of all, let's look at this AN minus 1. Let's put an arrow across there. So we have AN minus 1. This is equal to, well, this is going to be minus 1 here. So the top is going to be, instead of Fn plus 1, so Fn plus 1 minus 1, Fn, and the bottom is going to be Fn minus 1. So we just replace n with n minus 1, like that. And now Fn, recall Fn is just equal to, well, that's just the Fibonacci sequence, and scroll up. Fibonacci sequence again is just Fn equals Fn minus 1 plus Fn minus 2, for n is greater than or equal to 3. So we have Fn minus 1 plus Fn minus 2 over Fn minus 1. Yeah, so that's just the Fibonacci sequence on top. So now this equals to, well, divide this out. This is going to be Fn minus 1 divided by Fn minus 1 plus Fn minus 2 divided by Fn minus 1. So this cancels, becomes 1. So what we get is equals to 1 plus Fn minus 2 over Fn minus 1. And what I'll do here now is I'm going to multiply the top and bottom by, well, this power right here, 1 over Fn minus 2, because remember we want to show it's like that. So then we're going to try to get rid of this, make it a 1, so get rid of the numerator by dividing by it on both sides, top and bottom. Fn minus 2. So then what we end up having is 1 plus, then this 1 cancels, we get a 1. So 1 plus 1 over, then we have this Fn minus 1 divided by Fn minus 2. And now this Fn minus 1 divided by Fn minus 2, well, we know that Fn plus 1 divided by Fn is equal to An. So, and then we subtract one more, we get fn over fn minus 1, but this is fn minus 1 over fn minus 2. So in other words, this just becomes fn minus, this just becomes an minus 2. So add another one, so fn minus 1, fn minus 2. So this becomes an minus 1, minus 2, an minus 2. So thus, an minus 1 equals to 1 plus 1 over, so 1 plus 1 over an minus 2. So there it is. We've proven this so far, yeah. And that's exactly what we've proven over there, as I written above here. Yeah, so we just proved that. Now we're assuming that an is convergent, find its limit. So let's find the limit now. Alright, so now if we want to get the limit of this one, so we know that the limit exists, so we are given that the limit, the limit exists, in other words, it's convergent. So what we'll do is write, so if limit as n approaches infinity of an is equal to L, then by the earlier theorem, then basically this limit, limit as n approaches infinity of an minus 1, this also is going to equal L, and this also equals to limit as n approaches infinity of an minus 2. And this is from the theorem that I just went over. What was that? It was a theorem, theorem 2, I believe. Scroll above, actually no, theorem 3. Actually no, neither theorem 1 or 2. And from exercise 1, remember this one here, the limit as n approaches infinity of an plus 1 equals the limit as n approaches infinity of an. And again, you could just see this one here, instead of having a plus 1, we could have had a minus 1, would have been exactly the same thing. We're just going to have m would be n plus 1, and so on. So it's exactly the same thing, doesn't matter what it is. They're still approaching infinity, or approaching the limit. So the limit is being approached regardless where your initial starting point is. Yeah, so from exercise 1, I'll just put a bracket. From exercise X, or just from exercise 1, and also just using a bit of deduction. Yeah, so that's what we have is, well, we take this an from above, so thus limit as an minus 1, limit as n approaches 0. My bad. N approaches infinity, not 0, as limit as n approaches infinity of an minus 1. This equals to L, which equals to, over there, this entire limit as n approaches infinity of 1 plus 1 over an minus 2. So in other words, what we end up having is, this becomes limit of this one using limit laws, and then we just get the equation L equals to 1 plus 1 over L. And now multiply both sides by L, and what we end up having is multiplied by L on both sides, so that nothing changes. We end up getting is L squared equals to L, and then this one cancels now, plus 1. So just move this onto the move the other ones to the other side, like that. What we end up having is, I'll put the 0 on the other side, or I should put it this way, 0 equals to L squared minus L minus 1. Or just put it the other side for convenience. So we have it like that, so L is going to be on the other side. 0 is going to be on the other side. L squared, I move everything here, minus that, we have this. So, yeah, and so now what we could do is, well, recall the quadratic formula again, just copy and paste it from the one I've written above. So what we have is L is going to equal to, over here, where now B is negative 1, so we're going to have a negative of a negative 1, plus or minus square root of a negative 1 squared, minus 4, and then A, which is 1, then times it by C, which is negative 1. Like that, all divide this by 2 times A, which is 1. And then this equals to, well, negative 1 times negative 1 is plus 1. Then we have plus or minus square root, now we have negative 1 squared is 1. Minus 4 times 1 times negative 1, this becomes positive. And that becomes, well, plus 4. Like that, plus 4 over 2, and again, this just becomes 5, just save time. And there is our answer. This equals to the limit. Actually, no, it doesn't equal limit because we have the plus or minus. Yeah, so it's plus or minus, so thus L has to be positive, so we take this one here. Thus, L equals to 1 plus square root 5 over 2. And put in a bracket, oh, just put here, since L must be positive. Like that. A number, it's a number of, yeah, it's a number of rabbit pairs. That all's positive. You can have a negative rabbit pair. And again, yeah, scroll up here. So yeah, this basically part B was just giving us a easy way to find the limit by showing that it's you could write it in this form and use the exercise one theorem that I covered. So now, yeah, the actual numerical answer to this limit is actually very interesting and very important in mathematics. L equals to, if we put this in my built-in one-note calculator, 1 plus square root 5, all brackets, close brackets, divided by 2 equals 1.618033988749895. Alright, so finally finished all of the exercise examples and going over the concepts of sequences. So now let's finally just end this video off with just a brief mainstream history of Fibonacci and more. Very interesting stuff. Yeah, it's just it's been a habit that I've been going over in my earlier videos. Whenever I cover a concept in mathematics, I would like to go discuss the mainstream history behind it and behind the people behind it. Very interesting stuff, so I'll continue with that theme. So let's dive into here. So on Wikipedia for Fibonacci, let's read up on him. So Fibonacci, born in 1175 Common Era or AD, and then he died around 1250 Common Era. Was an Italian mathematician from the Republic of Pisa, considered to be the most talented Western mathematician of the Middle Ages. The name he is commonly called Fibonacci, or Italian Fibonacci, was made up in 1838 by the Franco-Italian historian Guillaume Libri, and is short for Filius Bonacci, son of the Bonacci, and he also is known as Leonardo Bonacci, Leonardo of Pisa, Leonardo Pisano Bigello, or Leonardo Fibonacci. So yeah, so the name is apparently made up. Very, very interesting. But anyways, going further, Fibonacci popularized the Hindu-Arabic numeral system in the Western world, primarily through his composition in 1202 of Liber Abazi, Book of Calculation. He also introduced Europe to the sequence of Fibonacci numbers, which he used as an example in Liber Abazi. So here's an image, here's a statue of him, zoom in there, very interesting statue of Fibonacci. He's got a pretty nice robe. It's going over, so statue of Fibonacci 1863 by Giovanni Paganazzi in the Campanato di Pisa. So you're born 1175 Common Era in Pisa in Italy. And he died most likely 1240 to 50, most likely in Pisa. Occupation mathematician, and he was known for Liber Abazi, popularizing the Hindu-Arabic numeral system in Europe, Fibonacci numbers, and his parents was Guglielmo. That's hard to pronounce. So history: Fibonacci was born around 1175 to Guglielmo, a wealthy Italian merchant, and by some accounts the consul for Pisa. Guglielmo directed a trading post in Bugia, a port in the Almohad dynasty's Sultanate in North Africa. Fibonacci traveled with him as a young boy, and it was in Bugia, now Bajaji, Algeria, that he learned about the Hindu-Arabic numeral system. So yeah, Fibonacci traveled extensively around the Mediterranean coast, meeting with many merchants and learning about their systems of doing arithmetic. He soon realized the many advantages of the Hindu-Arabic system. In 1202, he completed the Liber Abazi, Book of Abacus, or Book of Calculation, which popularized the Hindu-Arabic numerals in Europe. Fibonacci became a guest of Emperor Frederick II, who enjoyed mathematics and science. In 1240, the Republic of Pisa honored Fibonacci, referred to as Leonardo Bigello, by granting him a salary in a decree that recognized him for the services that he had given to the city as an advisor on matters of accounting and instruction to citizens. The date of Fibonacci's death is not known, but it has been estimated to be between 1240 and 1250, and most likely in Pisa. So Liber Abazi 1202 is the main article if you want to go read that on Wikipedia. So in the Liber Abazi 1202, Fibonacci introduced the so-called modus modus interum method of the Indians, today known as the Hindu-Arabic numeral system. 1202, so his birthday, he was born in 1175, so I believe that's about 27 years old. It's interesting. So the book advocated numeration with the digits 0 to 9 and place value. The book showed the practical use and value of the new Hindu-Arabic numeral system by applying the numerals to commercial bookkeeping, converting weights and measures, calculations of interest, money changing, and other applications. The book was well received throughout educated Europe and had a profound impact on European thought. No copies of the 1202 edition are known to exist. The 1228 edition, however, first section introduces the Hindu-Arabic numeral system and compares the system with other systems such as Roman numerals and the methods to convert the other numeral systems into Hindu-Arabic numerals. Replacing the Roman numeral system is ancient Egyptian multiplication method, and using an abacus for calculations with a Hindu-Arabic numeral system was an advance in making business calculations easier and faster, which led to the growth of banking and accounting in Europe. The second section explains the uses of Hindu-Arabic numerals in business, for example, converting different currencies and calculating profit and interest, which were important to the growing banking industry. The book also discusses rational numbers and prime numbers. So here's a page from his 1228 edition of the book. So a page of Fibonacci's Liber Abbasi from the Bibliothèque Nationale de Firenze, shown in box on the right. The Fibonacci sequence with a position in the sequence labeled in Roman numerals and a value in Hindu-Arabic numerals. And and I believe there's a 1228 edition now, but it could be a different edition. But anyways, so we have scanned copy here, and so I believe these ones would be the Roman numerals. I'm not sure which ones. Those are probably some of these ones, different lettering here, and then I believe these are the Indian numbers similar to ours, 1, 2, 3, 4 to 9. I believe that's a 144. I'm not sure. I believe they're just different numbers for theirs. But yes, very, very interesting stuff here. Let's just continue further into this. So now let's look at the Fibonacci sequence. And there you can read more main article Fibonacci number. I'll cover that actually in a bit. So Liber Abbasi posed and solved a problem involving the growth of a population of rabbits based on idealized assumptions. The solution generation by generation was a sequence of numbers later known as Fibonacci numbers. Although Fibonacci's Liber Abbasi contains the earliest known description of the sequence outside of India, the sequence has been noted by Indian mathematicians as early as the 6th century. Fascinating. In the Fibonacci sequence of numbers, each number is the sum of the previous two numbers. Fibonacci began the sequence not with 0, 1, 1, 2 as modern mathematicians do, but with 1, 1, 2, etc. He carried the calculation up to the 13th place, and then 14th in modern computing, because that is at 0. The 0 adds an extra layer there. So that is 2, 3, 3. Though another manuscript carries it to the next place, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377. And Fibonacci did not speak about the golden ratio as a limit of the ratio of consecutive numbers in the sequence. Very interesting, yes, and I'll explain the golden ratio soon, as I illustrated earlier above as well. So legacy. In the 19th century, a statue of Fibonacci was constructed and raised in Pisa. Today it is located in the western gallery of the Camp Ozzanato historical cemetery on the Piazza di Miracoli. Interesting stuff here, guys. So here's just an image from him I found on a mainstream news site, express.co. UK is drawing or a photograph of him. So this is Fibonacci. I believe he was 27 when he wrote that book. It's probably younger image of him. So now let's quickly go over some of the mainstream history and overview of the Fibonacci sequence and its close relationship with the golden ratio. Hashtag fascinating stuff. So going further. So it's from Wikipedia, Fibonacci numbers. So in mathematics, the Fibonacci numbers are the numbers in the following integer sequence called the Fibonacci sequence, and characterized by the fact that every number after the first two is the sum of the preceding one. So 1, 1. So 1, 1, then we have 2. Then again, we have 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So we have it all the way like that. Alright, so now often, especially in modern usage, the sequence is extended by one more initial digit, and that's adding a 0 there. So again, this 1, 1 is the sum of 0 and 1, and so on. So by definition, the first two numbers in the Fibonacci sequence are either 1 and 1 or 0 and 1, depending on the chosen starting point of the sequence, and each subsequent number in the sum of the previous two. is the sum of the previous two. So the sequence Fn of Fibonacci numbers is defined by the recursion relation as I went over, and that is basically Fn equals Fn minus 1 plus Fn minus 2, or F0 equals 1. Actually, whoops, I just thoughtlessly read that one out. So yeah, so it's this sequence with seed values, or the initial values, F1 equals 1 and F2 equals 1, or for modern usage, or modern computing usage, usually it's F0 equals 0 and F1 equals 1. And now here is a tiling with squares whose side lengths are successive Fibonacci numbers. So we have 1, 1, and 2, then go to the side 3, then you go to 5, then you go to 8 like this, then you go to 13. It's very interesting. These are the side length. Yeah, so I believe these are the these are squares. So each one is 13. So this is gonna be 13 like that, and so on. That is very interesting how they all line up perfectly like that. Then it goes all the way to 21, and 21 lines up with that as well. That's actually very, very amazing. Yeah, so yeah, I just want to add a quick note there. So yeah, very interesting how the side lengths match up with the previous squares as they spiral around. Very interesting like that. That's actually quite fascinating stuff. And here's further. Here's a Fibonacci spiral, which is an approximation to the golden spiral created by drawing circular arcs connected at the opposite corners of squares in the Fibonacci tiling. So these are the opposite corners, like that goes to here, this goes to here, and you start off like that. Very, very fascinating stuff indeed. And this one uses squares of size 1, 1, 2, 3, 5, 8, 13, 21. Very fascinating stuff. So Fibonacci numbers appear to have first arisen in perhaps 200 BC in work by Pingala on enumerating possible patterns of poetry formed from syllables of two lengths. The Fibonacci sequence is named after Italian mathematician Leonardo of Pisa, known as Fibonacci. His 1202 book, Liber Abaci, introduced the sequence to Western European mathematics. Although the sequence had been described earlier in Indian mathematics, the sequence described in Liber Abaci began with F1 equals 1. Fibonacci numbers were later independently discussed by Johannes Kepler in 1611 in connection with approximations to the pentagon. So that's very fascinating too. Actually, gotta look into that. So their reoccurrence relation appears to have been understood from the early 1600s, but it has been only in the past very few decades that they have in general become widely discussed. Interesting. So they are intimately connected with the golden ratio. For example, the closest rational approximations to the golden ratio are 2 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, and so on. That's fascinating. So you see the Fibonacci numbers there: 2, 3, then 5, then 8, and so on. That's actually very amazing. So Fibonacci numbers appear unexpectedly often in mathematics, so much so that there is an entire journal dedicated to their study, the Fibonacci Quarterly. Applications of Fibonacci numbers include computer algorithms such as the Fibonacci search technique and the Fibonacci heap data structure, and graphs called Fibonacci cubes used for interconnecting parallel and distributed systems. Very, very fascinating. They also appear in biological settings such as branching in leaves, phyllotaxis, the arrangement of leaves on a stem, the fruit sprouts of a pineapple, the flowering of an artichoke, an uncurling fern, and the arrangement of a pine cone's bracts. So yes, you'll see this everywhere. And the Fibonacci numbers are the sums of the shallow diagonals shown in red of Pascal's triangle. So notice how this goes up to 1. So this one here, if you have 1, this is going to be 1. It'll be sum of 0 and 1. And this one here, sum of 1 and 0. And then if you have over here 2, it's going to be sum of 1 plus 1 is 2. And then the 3 is going to be 1 plus 2 is 3. The 6, as you can see, is the sum of the top two. So 3 and 3 is 6. So you go to here 35, 20 plus 15 is 35. And here if you sum all these shallow angles, it's actually pretty amazing. Shallow diagonals, you get 1. Then you get 1 again, then you get here 2, then you get this, wow, that's amazing, 2, 1, that's 3, then 5, 8, 13, 21, 34, 55. So yes, that's absolutely fascinating. So now let's look at the golden ratio and go over here. And let's read up on this. So in mathematics, two quantities are in the golden ratio if the ratio is the same as the ratio of their sum to the larger of the two quantities. And the figure on the right, it's actually below, illustrates a geometric relationship. Expressed algebraically for quantities a and b, with a greater than b greater than 0, we have over here a plus b over a. If it equals to a over b, then this is by definition phi. This is phi, or the golden ratio, where the Greek letter phi, written like this, lowercase phi or phi, represents the golden ratio. It is an irrational number with a value of, and this is exactly the one I calculated in exercise 5. So 1 plus square root 5 divided by 2 equals 1.61803398887. And let me just note, this is the limit of the ratio of successive numbers of the Fibonacci sequence in exercise 4. And now remember, exercise 4, I just want to scroll up quickly because I think I may have mentioned earlier that the limit of the sequence is golden ratio, but that's actually not the case. It's the ratio. So here, remember here, so we let an equals to fn plus 1 divided by fn, like that. So that's the ratio of the successive terms of the Fibonacci sequence. But the Fibonacci sequence, the limit just keeps getting larger and larger, so it's infinity. So yes, so it's the ratio. And I showed here, then when you do the ratio, then it becomes like this, 1.618. So yes, fascinating stuff indeed. Let's just go back over here to the golden ratio. Yeah, so the golden ratio is called the golden mean or golden section, in Latin sectio aurea. Other names include extreme and mean ratio, medial section, divine proportion, divine section, or Latin sectio divina, golden proportion, golden cut, and golden number. Mathematicians since Euclid have studied the properties of the golden ratio, including its appearance in the dimensions of a regular pentagon. So you have to dig into that, it's very fascinating. And in a golden rectangle, which may be cut into a square and a smaller rectangle with the same aspect ratio. The golden ratio has also been used. It has been used to analyze proportions of natural objects such as as well as man-made systems such as financial markets, in some cases based on dubious fits to data. So yes, interesting. So the golden ratio appears in some patterns in nature, including the spiral arrangements of leaves and other plant parts. Some 20th century artists and architects, including Le Corbusier and Salvador Dali, have proportioned their works to approximate the golden ratio, especially in the form of the golden rectangle, in which the ratio of the longer side to the shorter side is the golden ratio. And believing this proportion to be aesthetically pleasing. So here is line segments in the golden ratio. So you have A and B, where the summation A plus B divided by A is, so A plus B is to A as A is to B. So it's the same ratio. And here's the golden rectangle with longer side A and shorter side B. When placed adjacent to a square with side lengths A and B, to side lengths A, will produce a similar golden rectangle with longer side A plus B and shorter side A. So yes, we have a golden rectangle over here, so A plus B over A. That's the golden rectangle, as well as A over B. So A over B, golden rectangle, and then the overall one is going to be golden rectangle. Put both of them together. And also what you could do here, now what I'm going to do is, well, I'm going to divide this out by, B. So if we divide it out by B, I'll just divide every single side. We're going to get a smaller rectangle, obviously, just to illustrate it. So what we'll have is B over B is 1. A over B is phi. And then over here is going to be, well, phi, A over B. And this is, well, A over B is equal to phi. So phi, so we have a square phi like that, and this is phi like that. So yes, there's one. That's phi. They're fascinating stuff. So going further, now relationship to Fibonacci sequence. The mathematics of the golden ratio and the Fibonacci sequence are intimately interconnected. The Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, 610, 987. And a closed form expression for the Fibonacci sequence involves the golden ratio, and you can write it like this: Fn equals to, when you simplify it, phi n minus negative phi to the power of negative n divided by a square root 5. So the golden ratio is the limit of the ratios of successive terms of the Fibonacci sequence, or any Fibonacci-like sequence as originally shown by Kepler. So the limit as n approaches infinity of Fn plus 1 divided by Fn equals to phi, as I showed. This is exactly exercise 4. In other words, if a Fibonacci number is divided by its immediate predecessor in the sequence, the quotient approximates phi. For example, 987 over 610 is going to be roughly equal to phi, like that. and so on. So for example, 2 over 1 is going to be, well, it's going to be 2. So then 3 over 2 will be 1.5. So it gets closer and closer to that number. And then 5 over, what's 5 over 3? That is, let's see what 5 over 3 is. So I'm going to type it in quickly. 5 over 3 equals 1.667, and so on. So that's fascinating. Then 8 over 5 equals 1.6. So yes, you'll eventually get closer and closer. And there it is, numbers in the in the later parts in the Fibonacci sequence. So it's fascinating stuff indeed. So these approximations are all alternately lower and higher than phi and converge to phi as the Fibonacci sequence increase. So yes, they alternate. That's pretty amazing. Let me just type that in over here actually. Yeah, note here, I just want to illustrate this further. So in MES note, here's the Fibonacci sequence, and here is phi. So let's just remove this dot. Yeah, so put phi over there, and let's see what happens when you do the term. So 1 over 1, that is obviously... So yeah, now we have over here, so 1 over 1 is 1, 2 over 1 is equal to 2, and then going further here, we have 3. So then the next one is 3 over 2. Let's see how it looks like. And the next one is, we have, it's 5 over 3. And the next one is, we have, let's remove the spaces. So now we have, next one is 8 over 5 equals 1.6. And then we have, next one is 13 over 8. And the next one we have is 21 over 13. So yeah, you can see it's it's going above and below the 1.618. So initially it's below, above, below, above, below, and then this one's going to be above, and then this is below, and then the next one, yeah, this is very, very fascinating stuff. The next one is 34 divided by 21. Now we have, this is above 1.618. And then we have 55 over 89 equals, the other way around, we have 55 over 34. Over 34. And this equals, below. And then we have, next one, 89. Yeah, 89 over 55 equals 1.618. That's a bit higher. So there's 1.6182. And then keep going on. This is pretty fun. So 114 over 89 equals 1 point. Actually, yeah, that's off. So 144, like that. So yeah, 1.618, and then 233 over 144. Yeah, it's getting pretty cool. And then 377 divided by 233 equals 1.618, and then let's see, I think my calculator is rounding up. 610 over 377 equals, yeah, it's just rounding up, and so on, so on. Yeah, so it actually just rounds up and so on. But what we could do here is now, I'll put the space here. So instead of, I could just type in pi, and also you could just put equals, and equals there. This is capital letter, I just made it capitals. And there it is, there is phi. Fascinating stuff indeed. And I'll erase the last digit, so because it sums up, and just put a dot, dot, dot. Because yeah, otherwise it would round up. So yeah, because 8, 9, and there's the 5 actually. Actually, that's not the exact phi. Let's see what the exact phi is. And the exact phi is, yeah, 887. We have 887, yeah, that's already rounded up. So anyways, that was just a sidetrack. Just wanted to get in those. I didn't realize it alternates like that. And it was very fascinating stuff. So now let's look at the golden angle. So in geometry, the golden angle is the smaller of the two angles created by sectioning the circumference of a circle according to the golden ratio. That is, into two arcs such that the ratio of the length of the larger arc to the length of the smaller arc is the same as the ratio of the full circumference to the length of the larger arc. Very, very fascinating. So yeah, basically, we're going to do the same thing with arc lengths. So the total to the larger, and it's the larger to the smaller. So that's all it is. So algebraically, let A plus B be the circumference of a circle, divided into a longer arc of length A and a smaller arc of length B, such that, so you have two arcs that form one full circumference, and then we have the golden ratio over here equals to phi. And the golden, golden angle here. The golden angle is the, actually no, the golden angle is not going to be like that. I mean, this is phi, this ratio is phi, but then the golden angle is going to be the angle subtended by the smaller arc of length B. It measures approximately 137.5077, etc. Or in radians 2.3999, and so on. It's fascinating stuff. And the name comes from the golden angle's connection to the golden ratio. The exact value of the golden angle is, and you can type it here, 360 divided by 1 minus 1 over phi. Oh yeah, let's put this phi, that's phi. And so on. And you get this degrees about 180 times 3 minus square root 5, and so on, or 360 divided by phi squared. Or in radians, 2 pi over phi squared. So yes, fascinating stuff indeed. So here it is, if you were to draw this out. So where the equivalents follow from well-known algebraic properties of the golden ratio. So here's the golden angle. Is the angle subtended by the smaller red arc. So there is our 137 ... degrees. When two arcs that make up a circle are in the golden ratio. So there we're going to have the golden ratio across there. So again, A plus B over A equals A over B. So it's fascinating stuff indeed. And now here's an example of the angle between successive florets in some flowers is the golden angle. So if you have one, it's going to be 137. Then the next one, so there's 1, there's 2, there's 3, and so on. Then there's going to go to the 4 here. Then go 4 is going to go to the 5. 5 is going to go to the 6. 6 is going to go to the 7, 8, 9, 10. Fascinating, fascinating stuff. So as you see it everywhere. So the angle between them are all going there. So now let's look at the golden spiral. So in geometry, a golden spiral is a logarithmic spiral whose growth factor is phi, the golden ratio. That is, a golden spiral gets wider or further from its origin by a factor of phi for every quarter it turns. And this is in polar coordinates. A golden spiral with initial radius 1 has the following polar equation: r equals phi to the power of the angle theta times 2 over pi. And that's in radians. So yes, then what you end up having is this spiral across like that, where, again, where's definition here? So it gets further from the origin by a factor of phi for every quarter turn it makes. So yes, if it goes here, a quarter is going to go across there, a quarter is going to go across there, and it goes further by a factor of phi. So yes, it looks like that phi, it looks like the approximation to it, the Fibonacci spiral. So yeah, golden spiral, assuming a square has a side length of 1, the next smaller square is 1 over phi wide, the next width is 1 over phi squared. Yeah, this is the next smaller one, so yeah, each one's width is going to be 1 over phi squared and 1 over phi cubed. So on, it's very interesting stuff. And here's the Fibonacci spiral, approximates a golden spiral using quarter circles inscribed in squares of integer Fibonacci numbers, shown again, this is similar to one above, 1, 1, 2, 3, 5, 8, 13, and 21, and so on. So this looks like that spiral there. Very fascinating stuff. I can find a good comparison between the two, but it may be in later videos. So anyways, finally, let's go over some golden and Fibonacci spirals in nature and art, design, corporations, even advertising, and Fibonacci sequences, and so on. So here's a galaxy, goes spiral like that. Very fascinating stuff. There's a hurricane, and there is a flower. And there is another leaves like that going in there. There's a shell, some other leaves or some other plants like that. And here is this is a model of the spiral. And here is another flower inside. And here's even water. Water is spinning in a vortex. That's following it looks like a spiral, Fibonacci / golden ratio. And here is this a snail. Here's some grass. Hurricane from above, there's a seahorse, and so on. And these, even the sequences of tree branches, you got 1, 1, and you have 2, 3, 5, 8. Yeah, I believe these are the lengths. This one has 1, this one has 2, this one has 3, then it has 5, then it has 8, and so on. And each one breaks up into it like that, and so on. Very fascinating stuff. Not exactly sure about the details, but yes, very fascinating. Here's some pineapples grow in a numerical sequence as well. And here's how hard to zoom in. So 8 parallel rows. So it has 8 parallel rows this way, of scaling spiral gradually, and it has 13 parallel rows spiraling at a medium slope like this, and it also has 21 parallel rows of scale spiraling steeply all the way across. Fascinating stuff. And you have 1, 2, 3, 5, and then there's 8, 13, 21. And consider the drawing of a pineapple here, where we have numbered the hexagons. The numbering has been done by the following rule. The lowest hexagon was assigned to 0, 0, and then the next higher gets a 1. Remember, this continues on the backside, not visible in the picture. Then the next higher is assigned the number 2, and so on. Notice the hexagon 42 is slightly higher than hexagon 37. Yeah, where's the 42? 42 is slightly higher than 37. And basically, yeah, right here you should be able to identify 3 distinct spirals. One will have the hexagon 0, 5, 10. So where is the 0, 5, 10? So 0, 5, yeah, 10. I believe the 10 is on this side there. And the spirals like that. The second will have hexagon 0, 13. So there's a 0, 13, 26 going upwards like that. And the third will include 0, 8, 16. So 0, 8, 16. So basically similar to one above, we have a horizontal, we have a medium slope, and then we have a very steep slope up top there and there. And now look at the common difference between the spirals, and you will find a difference between 5, 18, 13. Yeah, 5, 8, and 13. So there's 5 this way. There is, and this one is a bit smaller than the other one. And this one's going to be 8. It's going to be 13 across. It's going to be 13 across there. This should be. So this one follows a 5, 18, 13 over here, but then this pineapple is, I believe, is bigger relative to its the hexagons, and those go 8, 13, 21. So anyways, that's very interesting. Yeah, very interesting pineapple Fibonacci sequence. So yeah, there's this way, and then there's the vertical one. So yes, count them up next time you eat a pineapple. Here's an egg, also Fibonacci sequence across there. Let's see, here's even continents. You could see Africa like that, starting from there and goes all the way down. Very fascinating stuff. There's the Mona Lisa. Very fascinating stuff indeed. So going further, this is Sonic the Hedgehog. And there's even websites can also have it visually set up like that. So little tabs on top there, and then scrolls over for the big main stuff that you got to look at, the main article. So there's National Geographic. You could also see it has one there. Here's another website here. And yeah, so there it is to set up in all these blocks and Fibonacci blocks. And even here, this is even movie covers. You can see, yeah, you can see the kind of spiral here across, and there's a spiral across there. And yeah, it's very, very fascinating stuff. And here is a Dream Piano advertisement. There it is, the Fibonacci sequence as well. It just it looks cool, and yeah, I believe Apple logo probably has it too. Yes, very interesting stuff here. I haven't confirmed, but it looks like it. You got a bunch of spirals here, and yeah, and even a ball thrown in a wet tennis ball like that, spiraling across. There's Fibonacci in the waves. There's Fibonacci hurricane, galaxies, and even Trump's hair. So yes, yeah, pretty cool stuff. So yes, let's just scroll all the way up in here. It's just very fascinating stuff. So yes, that is all for today. Hopefully follow along this entire extensive video. Let me know if I made any errors or mistakes or anything in here, because it's a very, very long video. And yeah, I just noticed a mistake here. I believe some of the text got jumbled up. I'll fix that soon. But yeah, it looks like these ones were fine. Yeah, this was had an issue. I'm just going to pause the video and fix it right now. Yeah, and here I quickly unpaused it, and there I just fixed up. I just had it had... Yeah, because my initial notes got replaced over top. They disappeared, and then when I was wondering where they went, and they just came back now. So let's remove those behind it. So anyways, there it is. It looks fine now. So yeah, that was all for today. Sorry about that, but let me know if there's any other mistakes in this video, and I'll jump right ahead and we'll make a correction in the video or in the description below, and so on. So anyways, very, very extensive. I'm just going to scroll all the way back up, see if there's any other mistakes or any other errors. So just very fascinating stuff. We'll follow along and absorb all of this information. And again, as I stated before, I'm doing these super long video styles just to give me more time to do what I've been doing in the background, which is researching free energy and anti-gravity, and pretty much all topics in, because once you realize the mainstream is mainstream of everything, politics, news, science, it's not fully there. So then you gotta either find alternatives or develop your own science, and that's what I may have to do. Hashtag vortex math. But anyways, let's scroll up, and here's another note that I just corrected here, and we'll see if I might just redo the initial part of the video as well. So phi is a limit of the ratio, of successive numbers of the Fibonacci sequence, and not before I may have stated a couple times that it was the limit of the sequence, but no, the limit is infinity. Anyways, that's table of contents, and here's a top secret financial advice, or occult financial advice. Top secret, guys. This will make more sense when I finish my part 6 anti-gravity video. But anyways, remember the phrase, the ripple in the aether of duality. And these top 3 cryptos are probably going to be the top 3, but in varying orders. I think Ripple might be number 1 in a bit. But in any case, I believe the top 3, these are pretty much established, and they'll be there for several years at least, many years maybe. But anyways, I'll let you know if anything changes. And that's all for today. Like always, you can download these notes and these exact ones in the link in the description below, as well as viewing these notes all in article format on Steemit. Follow me at MES, and make sure to check out my cool math forums on Reddit and vote. Anyways, that's all for today. Thanks for watching, and stay tuned for another math easy solution.